We believe that the world acts in ways that we can see, test, and explain. But there is a deep question beneath that certainty. Why does nature follow rules at all? Why isn't reality just a swirling mess of nonsense that doesn't follow any rules or patterns? There is a very important question in physics that this video goes into great detail. Why are there rules in the first place? We will look at the secret symmetries that form particles and the mathematical structures that seem to control everything. This is where the order in the universe starts. It's not enough to just know what the rules are. The hard part is figuring out why they work. The invariance principle: why physics works everywhere. You could drop a ball in New York and expect it to bounce the same way on the moon, which it does. That's because the basic rules of physics don't depend on where you are. They stay the same. They are true everywhere in the universe, from the tip of your pen to the center of galaxies far away. Universality means that the rules of the game don't change from place to place or time to time. This idea is called the invariance principle. And it's the secret that shows reality is not a mishmash of local oddities, but a complex, consistent fabric. This consistency arises because there's no preferred position or moment in the universe. Move your experiment, change its orientation, or run it at a different instant, and you'll get identical results. That holds whether you're measuring the electron's charge, the energy of a photon, or the gravitational pull of an apple. The same equations govern all systems everywhere, and this symmetry underpins the uniformity of the cosmos we know. The idea of invariance is very strong. It's not enough to say physics works everywhere. Because of the way math works, physics has to work everywhere. If it didn't, the universe would act randomly. Galaxies could form in one spot and fall apart in another. That would mess up the patterns we use to figure out where we fit in the universe. We test invariance every day by moving systems around. In particle accelerators, we pummel protons at high energies and get the same interaction behaviors no matter where the accelerator sits. If a detector in Europe suddenly stopped turning up moons while the one in Japan didn't, we'd know something had gone fundamentally wrong. But it doesn't. Every station, every telescope, every instrument agrees. We live in a universe that plays by one unified set of rules. Notably, Einstein's relativity owes everything to invariance. He insisted that the laws of physics, including the forever constant speed of light, must look the same to all observers regardless of how they're moving. That principle birthed a revolution. Simultaneity shredded, space and time fused into one dynamic fabric, gravity reframed as geometry. All because physics is invariant under motion. But invariance is more than that. It has a direct link to the rules we count on for conservation. Energy must be kept the same because physical rules don't change over time. Momentum stays the same in space because things don't move. Be sure to read the next chapter, because Emmy Noether will use math to explain that link. The invariance principle also explains why science is universal. Astronomers, chemists, and engineers build telescopes that pry deep into the early universe. The patterns they spot, the behaviors they measure, all obey the same laws that keep your phone battery working. Without invariance, there'd be no basis for trusting observations from a probe like the Webb or a rover on Mars. Invariance means our models aren't local snapshots. They're global truths. But how deep does this invariance go? Does it hold everywhere for always? We don't know. Perhaps true invariance fails at extremes, near the Big Bang or at the core of quantum gravity. But until we find such a crack, it remains the most powerful glue binding reality together. One day, we might find that nature's ultimate invariances aren't so clear-cut, are only roughly true, or are even broken. But for now, every accuracy test supports them. It's not luck, it's a sign. The way nature is built tells us something. It's meant to communicate itself in a way that is consistent and in tune with itself. This leads to a very important conclusion. If physics is constant, then where something is doesn't matter. This means that you and a space alien from billions of light years away would still be able to measure gravity, electrons, and photons the same way. What they find in their physics lab would be the same as what you find in yours, even if they call their tools something different. Their DNA and society may be very different, but their atoms follow the same rules as yours. This uniformity in the universe is what gives science meaning. In other words, we're not just collecting local oddities, we're also figuring out global language. Space isn't made up of islands, and each one has its own rules of physics. There is only one environment, and the rules that govern it don't care about borders. Then why does physics always work? Because the world is based on invariance, which means that no experiment, direction, or epoch can change the way nature works. That's why we think stars will shine the same way in all space and time, why electrons have the same charge no matter where they are, and why you can study the tiniest particles on Earth and be sure that your conclusions will hold true at the edges of the universe that we can see. Symmetry in nature, the hidden blueprint behind laws. Spin a snowflake around. It looks the same whether you turn it 60 degrees or not. That's symmetry, which means that the item stays the same after the change. But in physics, symmetry isn't just about making shapes that look nice. It is what holds all the forces, equations, and particle interactions we have ever measured together. In fact, symmetry is so important that it's sometimes called the language of nature's rules, or the secret code that makes everything from electrons to galaxies make sense. In physics, symmetry means that a system remains unchanged under a certain transformation. That could be shifting a particle's position, rotating it, flipping it like a mirror image, or even swapping particles of matter with antimatter. If the equations that describe the system don't notice the change, if they still work perfectly, then that's a symmetry. Now, why is that a big deal? Because every symmetry implies something being conserved, some quantity that stays constant no matter how the system evolves. If the laws of physics don't change over time, then energy is conserved. If they don't change across space, momentum is conserved. If they don't change when you rotate a system, angular momentum is conserved. This deep connection between symmetry and conservation isn't just a nice coincidence. It's a formal mathematical truth, which we'll unpack more with Notha in the next chapter. Forces are also caused by symmetry. Take a moment to think about this. Electricity works because of how we handle electric charge. In the same way, the strong and weak nuclear forces come from more general inside-out imbalances. You can't picture these by turning something around or flipping it over in a mirror. They live in mathematical spaces instead, where things like charge, taste, and color, yes, quantum color exists, can change. As long as the equations stay the same, symmetry stays the same. And when the balance is lost, things start to get interesting after that. Most of the organization in our world comes from broken symmetry. In the early universe, all the forces may have worked together to make a single perfect unity. Those similarities broke apart as the universe cooled, though, and the separate forces we know today came into being. If you start with a perfect snowflake and slowly heat it up, the arms will melt away, leaving behind something new that isn't symmetrical but is stable. Bosons like electrons and quarks get their mass from this type of spontaneous symmetry breaking. The Higgs field, which did that, was balanced at first, but then it stopped being that way. Once that symmetry was broken, particles started to interact with the Higgs, and presto, mass showed up. But symmetry isn't just something that happens in particle physics or the early universe. It's everywhere. In chemistry, the shapes of molecules often follow symmetrical rules. In biology, animal patterns, from butterfly wings to zebra stripes, are governed by symmetrical development processes. Even in economics, certain models rely on symmetric assumptions about behavior and probability. Nature seems to prefer symmetry as a starting point, and only departs from it when there's something to gain, like structure, mass, or diversity. In mathematics, symmetry is tied to group theory, a branch of algebra that studies how transformations work. Every known force in physics can be described using symmetry groups. The standard model of particle physics is built entirely on these principles, using mathematical groups like SU3, SU2, and U1. Don't worry about the symbols. Just know that these groups describe how particles behave, how they interact, and how they're allowed to change without breaking the rules. The more we discover about the universe, the more it looks like symmetry isn't just a helpful tool. It might be the thing, the hidden scaffolding that reality is built on. If you were designing a universe from scratch and you wanted it to be stable, predictable, and rich with emergent behavior, you'd probably start by laying down symmetrical rules. Why do some symmetries exist and not others? Why is charge conserved, but not parity in weak interactions? Why do particles respect some kinds of mirror flips but ignore others? Nature seems to use symmetry selectively, and sometimes shatter it deliberately, as if following an unknown script that balances elegance with complexity. And this leads to one of the biggest questions in all of science. Are the laws of physics themselves the result of a deeper, more perfect symmetry? Maybe the universe we see, with its quirks and asymmetries, is just a broken version of a more symmetric reality that lies beneath, like a statue that was once whole but is now cracked and weathered by time. Noether's theorem, where laws come from in math. For every action there is an equal and opposite reaction, is a saying you may have heard. But what if we told you that nature has a protection rule for every symmetry, not only logically, but also mathematically? That's what Noether's theorem is all about. It's one of the most important ideas in theoretical physics. It came from the thought of Emmy Noether, a German mathematician whose ideas changed the way we think about the whole world in a quiet way. In the early 1900s, Albert Einstein had just unveiled general relativity, a bold new vision of gravity as geometry. But there was a problem. When you tried to apply the usual laws of conservation, like energy conservation, to Einstein's new framework, things got fuzzy. Physicists struggled to define what energy even meant in a curved, dynamic spacetime. Enter Noether. In 1915, Emmy Noether proved something astonishing. Every symmetry in a physical system corresponds to a conserved quantity. And this wasn't just a helpful observation, it was a rigorous mathematical fact. For example, if the laws of physics don't change over time, that is, they're symmetric under time translation, then energy must be conserved. If the laws don't change across space, spatial translation symmetry, then momentum is conserved. If they don't change when you rotate your system, rotational symmetry, then angular momentum is conserved. This trend holds truer the more you dig. How do you conserve charge? The field equations for electricity have something to do with that. Conservation laws can also be made from more complex symmetries, like those involving gauge transformations or internal quantum numbers, as long as they are continuous and differentiable. Why is Noether's theorem so strange? It doesn't just list the rules of physics, it also explains them. It tells us where these rules came from and why they are in place. Scientists knew that some numbers would stay the same before Noether. Once Noether was dead, everyone knew that conservation is a result of symmetry. You don't have to start with being environmentally friendly. When you do your trial, all you have to do is pretend that nature doesn't care. Conservation will come out on its own. Let's say you're making a physics engine for a video game. You don't have to write that rule by hand if you want a universe where energy stays the same. Just make sure that the engine doesn't treat each second differently and you'll get free energy saving. It's the same with room and speed. The rules are written by symmetry, and this goes beyond convenience. In quantum field theory, the framework behind the Standard Model, Noether's theorem is central. Every fundamental interaction is described by a symmetry group. Electromagnetism? That's U, one symmetry. The weak force? SU, 2. The strong force? SU, 3. These aren't just math tricks. They're how particles and forces exist in the first place. Noether's insight even shapes modern cosmology. For instance, inflationary theory, the idea that the early universe expanded faster than light, relies on the idea that vacuum symmetries can break, releasing energy and shaping the structure of space itself. Noether's fingerprints are all over that. If every symmetry gives rise to a conservation law, Then what happens when a symmetry breaks? That's when things get even more interesting. In physics, spontaneous symmetry breaking occurs when a system has symmetrical laws, but the solution doesn't reflect that symmetry. Think of a pencil balanced on its tip. The laws are symmetrical, but the moment it falls, it chooses a direction, breaking that symmetry. And when symmetries break, new things emerge. The Higgs mechanism, how particles get mass, comes from a broken symmetry. The diversity of particle types, the formation of atoms, even the structure of the universe itself, all can be traced back to moments where a perfect symmetry gave way to complexity. What about Emmy Noether? In her time, she had to deal with a lot of prejudice. She was very smart, but for many years she couldn't teach under her own name. She put out important work without giving thanks. Still, her efforts are now seen as some of the most important in the history of physics. Her work was called A Monument of Mathematical Thought by Einstein himself. Gauge fields, invisible structures that dictate forces. The world seems to be made up of things like planets, particles, atoms, and stars at first glance. Take a better look. If you take off the layers, you'll find something completely different. Fields that move through space that you can't see. There are fields that control all the forces you've ever felt. Gravity pulls you down. Magnetism spins a compass. Electricity sparks life into machines. But behind them, gauge fields. These aren't just background features. They are the hidden scaffolding of reality, mathematical structures that dictate how particles behave, how forces arise, and why the universe has order in the first place. A gauge field is a field defined by a symmetry, not of shapes, but of the rules themselves. It's like designing a game where players can wear any color, but the outcomes of the game don't change. That freedom to choose a color, that's a gauge symmetry. In physics, it's the freedom to transform a field locally, point by point, and still get the same physical result. And to preserve that freedom, the laws of nature are forced to include a gauge field. Electromagnetism is a well-known case. What is the electromagnetic force in quantum electrodynamics, QED? It comes from a U-1 gauge symmetry, which is a way for a quantum field to rotate freely. If you make this symmetry local, which means that each point in space can spin its field on its own, you find that a photon must appear. Yes, that is true. EM fields, which make light, Wi-Fi, and lightning possible, are not essential on their own. It happens because of a balance in the math behind it. This is true for all forces in the standard model. The weak force, it comes from an SU2 gauge symmetry. The strong force, SU3. These aren't just abstract terms. Each one describes how a field transforms and how particles respond. The particles that carry these forces, like W and Z bosons, gluons, or photons, are messengers of symmetry. So forces aren't just out there, they're enforced by symmetry, through fields. But what's the big deal? Gauge theories are shockingly powerful. They don't just describe forces, they predict them. Once you choose a symmetry group, the types of particles and their interactions fall out naturally. The math does the work. Want to describe the strong force that holds quarks inside protons? Just write down the Lagrangian with an SU3 gauge field, and boom, you get 8 gluons and a complex dance of color charge. The equations write the universe into existence. Gauge fields don't live in empty space, they shape it. In some quantum gravity theories, space-time itself may emerge from gauge interactions. In string theory, gauge fields are fundamental. Tiny strings vibrate not just in position, but in gauge space. In loop quantum gravity, the loops that weave space-time are traced by gauge connections. The geometry of reality and the structure of forces may not be separate. They may be the same thing, viewed from different angles. Gauge symmetry tells us that the laws of physics don't care about arbitrary choices. You can shift your reference frame, rotate a field, tweak a parameter, and the math still works. That flexibility is baked into reality. But for the math to remain consistent, nature demands compensation. That compensation, gauge fields. It's like tuning a piano. You can choose a new pitch for every note, but to keep the music coherent, you'll need to adjust the intervals. In physics, The intervals are the force fields. They exist to preserve harmony. There are times when gauge fields talk to each other. The strong force is made up of gluons, which are charged in their own field. That's why quarks are stuck inside hadrons and can't be taken out. As you pull them apart, the force gets stronger. On the other hand, electromagnetic fields don't associate with each other. That's why you can split the charges of electricity. The force's attitude is set by the framework of the gauge group. The Higgs field, on the other hand, might actually be a gauge field. It doesn't make sense. It gives things weight. People who can move around easily are free to do so, and it changes the way gauge bosons act in every way. W and Z bosons would have no mass if it wasn't for it. It gives them weight, and the weak force becomes, well, weak. Every time you experience gravity, electromagnetism, or nuclear forces, you're interacting with a gauge field. Every rule in nature, from how particles spin to how they scatter, is constrained by this invisible web of symmetry. But why do these specific gauge fields exist at all? Why SU, 3, SU, 2, and U, 1? Why do the equations need precisely these structures and not others? Physicists are still searching for that answer. Some think the symmetry is even larger, like SU, 5, or SO, 10, and gets broken down into the ones we see. Others look to string theory, where gauge groups emerge from the geometry of extra dimensions. Some even suspect that gauge symmetry is just a low-energy approximation of a deeper pre-space-time structure. Planck units, nature's built-in measurement system. We use made-up measures like meters, seconds, and tons to make sense of the world around us. But none of these are built into the world. They are made up by people and are based on random things like the length of a silver bar in France or the speed at which the Earth spins. Yes, it is useful. For everyone, not even close. What will happen if we take away all the societal supports? When we talk about the raw language of the universe, what units are left? That's where Planck units come in. Proposed by Max Planck in 1899, they represent a system of measurement that doesn't rely on human conventions at all. Instead, they're built from nature's fundamental constants, like the speed of light, Planck's constant, and the gravitational constant. These are the values the universe itself runs on. So when we measure something in Planck units, we're not asking, how long is this in meters? We're asking, how does this compare to the smallest, most basic structures reality allows? Take a look at the Planck length, which is about 1.6 times 10 to the minus 35.5 meters. It's so incredibly small. A proton is 100 million times bigger than this. It's not just a small amount, it's the most that can be done. Space itself starts to lose its sense below this size. There are quantum changes that are so strong that space-time could tear, fuzz, or fall apart completely. Many ideas say that the Planck length is the point at which the smooth structure of space breaks down into a frothy, uncertain mess. It's not just a short length of time. This is where mathematics ends. After that, there is Planck time, which is about 5.4 times 10 to the minus 44.4 seconds. In terms of physics, this is the smallest amount of time that makes sense. There are limits to how far you can go when you try to look into a shorter moment. You can measure the smallest where with the Planck length and the smallest when with the Planck time. Time doesn't tick below it. It stutters, jitters, or maybe doesn't exist at all. The Planck mass, meanwhile, is heavy, by particle physics standards anyway. It's around 22 micrograms, which sounds tiny, but is huge compared to things like electrons or quarks. This mass scale is especially important in quantum gravity. It's roughly the mass where quantum effects of gravity become non-negligible. In a sense, it's the point where particles are so massive and compact that they could form microscopic black holes. It marks the frontier between quantum mechanics and general relativity. These constants aren't just technicalities. They're the raw numbers that set the stage for every event in the universe. And when you combine them, Planck's constant, h, the speed of light, c, and Newton's gravitational constant, g, you don't just get weird math, you get a natural operating system. Unlike meters or pounds, Planck units mean the same thing anywhere. If an alien civilization on the other side of the universe built physics from scratch, they wouldn't use inches or feet, but they would know the Planck length. That's because it doesn't depend on the size of their planet, their language, or their biology. It only depends on how the universe itself behaves. Some physicists even think of Planck units as the code base of reality. Just as a video game has a smallest pixel or frame rate, the universe might have a fundamental resolution, and Planck scales define it. Anything smaller or faster just isn't supported by the system. But there's a deeper mystery here. Why do these constants have the values they do? Why is the speed of light around 300 million meters per second? Why is Planck's constant so small? If any of these values were even slightly different, the universe would be unrecognizable. Unstable atoms, no stars, no life. And yet, they are what they are. The Planck system doesn't explain why these constants have their values. It just shows how to combine them into something intrinsic. Planck units are, on the one hand, incredibly beautiful. They point to a universe that doesn't care what people want. A universe that can be understood in terms of what is true and what is false. On the other hand, they bring up questions that are concerning. Are these factors really that important? Or are they just placeholders, rough lines that point to a bigger idea we don't fully understand yet? Some scientists believe that the factors we know, like C, H, and G, may come from something greater. They could be scientific means or low-energy versions of things that are even more basic. These numbers may change at higher energies or in different parts of the universe. That would mean that the Planck system, even though it is very strong, only makes sense in a small area. It would be like a regional accent in the larger language of physics. Another thought is that reality might not be physical at all, but digital. Planck units could then stand for the tiniest bits, which are the parts of space, time, and mass that can't be broken up. Then physics would be a computer program, and Planck scales would show how far apart the grids are on the cosmic computer. In line with thoughts in quantum gravity, loop theory, or even simulation theories, this might make sense. So when we ask, what are the natural units of the universe? We're really asking, what are the assumptions baked into the operating system of everything? Planck units are like the default settings, the safe mode of physical law. And understanding them might be the key to rewriting the code. Yet for all their elegance, they remain mostly invisible. No experiment has ever directly probed the Planck scale. The energies required are far beyond anything we can generate. Black holes and the Big Bang are the only environments where these limits are truly felt. Why is there a speed limit? The origin of light speed. The speed limit in space is set and can't be changed. There is nothing that can move faster than the speed of light in a vacuum, which is about 299,792,458 meters per second. It doesn't matter how strong your rocket is, how much energy you put into a particle, or how crazy your ideas are. A little over 300,000 kilometers per second. No, it's not just the speed of light, it's the speed of everything in the universe. However, why is there even a limit? We need to change our ideas about what speed is in order to understand that. Newtonian physics says that speed is just space over time. It's easy to understand and can be scaled up or down indefinitely. Want to move faster? Just push harder. Increase your force and speed by 2 times. Special relativity, which Einstein came up with in 1905, broke that myth. Einstein proved that space and time are not 2 different things, but rather 2 parts of the same cloth called space-time. And that cloth has rules for it. Things move more slowly when they are pushed close to the speed of light. Mass goes up. When you get closer, it gets harder to add even a little more speed. When you're moving at 99.9999% of the speed of light, adding more energy doesn't change your speed much. It just makes you heavier. Light speed turns into a wall in space that no mass-carrying particle can pass. Why? Because the speed of light isn't just a speed. It's a ratio that defines the geometry of the universe. It links space and time in the equations of special relativity. Think of it like the conversion rate between meters and seconds. If space-time is the stage on which all physics plays out, then light speed is part of its scaffolding. Light itself isn't the reason for the limit. It just happens to travel at that limit. Photons, the particles of light, have no mass. That's why they can hit this cosmic speed without resistance. If massless particles didn't exist, we might never even know there was a speed limit. Light's just the most visible messenger. So this isn't about light being special. It's about the geometry of space-time being structured in such a way that massless things naturally move at this maximum rate. It's not something light does. It's something the universe is. This brings us to Maxwell's equations, formulated in the 1860s to describe how electric and magnetic fields behave. When James Clerk Maxwell solved them, he noticed something strange. They predicted that electromagnetic waves should always propagate at a specific speed. That speed, when calculated using known constants, turned out to be exactly the speed of light. Light is an electromagnetic wave. It's not just some mysterious glow. It's a vibration in the fabric of electric and magnetic fields. And those fields are governed by fundamental constants, specifically the vacuum permittivity and permeability. Put those together, and you get c, the speed of light. So, in a way, c isn't a speed, it's a consequence. It's the inevitable result of how fields ripple through the vacuum. Try to change the laws of electromagnetism and you'd change c. But do that, and the whole structure of space-time, and all the laws that rely on it, would unravel. However, that brings up another question. Why that number? What's wrong with going 1,000 kilometers per s, or a billion? Why approximately 300,000 km/s? No one really knows. If we change the measures from meters and seconds to something else, the number itself changes. We get a new value for c. In natural units like Planck units, it's 1 though, that is the 1. 1 meter per second, not 1. In that case, it means we're not looking at a random number, but a measure that's built into the very code of the universe. Some theorists think that c could be a kind of universal constant tied to causality itself. If information could travel faster than light, you'd open the door to paradoxes, messages from the future, events happening before their causes. Special relativity keeps the timeline stable. It protects the chain of cause and effect. Without a speed limit, time becomes a mess. Some ideas say that the speed of light might have been different in the early universe, which is even stranger. Theories about the changing speed of light say that c was much higher when the universe first started. This might help explain why the universe looks so orderly from very far away. Most of the time, inflation is blamed for that, but a changing c could also be to blame, though there isn't any strong experimental proof yet. There are also ideas that say light isn't the real limit. Even faster might be gravity waves or some other unknown force, but we have never seen any proof of this. The rule that c is the cap is proven by all observations in particle physics, astronomy, and gravitational waves. It is a law that the world follows without question. So what does it mean for us? It means we'll never visit the stars as quickly as we dream in science fiction. No warp drives, no hyperspace shortcuts, not unless we find loopholes, like wormholes or quantum tunneling. But until then, c is the ceiling. Standard model parameters. Who set the dials? It's like looking at a control board with a lot of dials that are all finely set to the same spot. These dials manage everything, from how electrons move around nuclei to how quarks stick together inside protons. They tell us how strong the basic forces are, how heavy particles are, and how they mix and break down. The strange part is that these dials exist. They're real. All of them are part of the Standard Model of particle physics. The Standard Model is the most successful framework we've ever built for describing the subatomic world. It describes 3 of the 4 known fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It includes all known elementary particles, like quarks, leptons, and bosons. It has survived every experiment we've thrown at it for half a century. Still, it has at least 19 free options. That means you have to type in the numbers by hand. They're not based on theory. At least not yet. They aren't based on deeper ideas. They're weighed, connected, assumed. There are 6 different quark masses, ranging from the very light up quark to the very heavy top quark, which is heavier than an entire gold atom. Then there are the lepton masses, which include the electron and its ghostly cousins, the tau and the muon. How come these values? Unknown. Then there are the coupling constants, the strength of the strong, weak, and electromagnetic forces. These define how particles interact, how likely they are to attract, repel, or transform. Even a tiny tweak would break everything. If the strong force was slightly weaker, protons wouldn't hold together. If electromagnetism was stronger, chemistry as we know it would collapse. There's also the Higgs field's vacuum expectation value, the amount by which the Higgs field leans into existence. This number determines how all particles get their mass. But why does the Higgs lean just enough to give electrons mass, but not enough to make light stop propagating? Again, no answer. The mixing angles show how particles change their names because of the weak force. The rules below describe how neutrinos can change types as they move through space. It's kind of like being able to switch passports while moving from one country to another. Easy to use, but strange. All of these factors make the standard model incredibly accurate. When you put them into equations, you can get results that are 10 decimal places off from what you saw in the tests. It's like having a great piano tune while it's storming outside. However, where did that string sound come from? One answer could be, there's no reason. In other words, these beliefs are just facts. The world is the way it is. It takes 0.511 mega electron volts to get an electron. But most physicists aren't satisfied with that. We want to know why. We want a theory that predicts these values, derives them from first principles. That's where ideas like grand unified theories, GUTS, and string theory come in. They try to go beyond the standard model by reducing the number of free parameters, tying them together with deeper mathematics. So far, though, no GUT has nailed it. And string theory? It suggests something even more unsettling, a landscape of possible universes, each one with different values for those parameters. In some, electrons are too heavy for atoms to form. In others, stars never ignite. Our universe is just one out of a near infinite multiverse, and we live here because it works. That's the case from anthropology. It says, don't ask why these dials are set to these numbers. Find out why they let life exist. What's the answer, since we're here to ask? To put it another way, it's not deep physics. It's cosmic selection bias. That tastes bad, though. It tastes like giving up on getting it. The universe must be tuned just right, so there must be a way to explain it, a greater theory. Our search takes us to running constants. Some factors don't stay the same. They change as energy changes them. One example is that the electric force gets stronger as it gets closer. If we could think ahead far enough, all the forces might come together at a very high energy level. That's the idea behind GUTS. But tests haven't shown it to be true yet. The fine-tuning itself is another obscure thing. Complex chemistry doesn't work if you change even a few factors, like how heavy the neutron is compared to the proton. That's it. Not a star, not us. Is that just a coincidence? Or a hint? Neutrinos should also be thought of. They have a very small mass, millions of times less than electrons. Why? Some models say that they get their mass from a very different source than other particles. That would mean that the standard model isn't the whole story if it were true. There are some corners missing from the piece. There's also speculation about moduli fields. In string theory, hidden variables that set these parameters during the early universe. If those fields settled into specific values after cosmic inflation, maybe that's what locked the dials into place. But this is theoretical scaffolding, with no experimental support, yet. The fine structure constant, a law with no reason. In science, there is a number that shows up all the time. It can be found in quantum physics, the structure of atoms, electromagnetism, and even the formulae that describe how light and matter interact. It's not a whole number. It's not based on a simple method. Still, it controls the strength of the electromagnetic force, which is probably the most important power for everything we see, feel, and live. That number is approximately 1 divided by 137. Technically, it's around 1 divided by 137.035999206. But most physicists just call it alpha, the fine structure constant. It's one of the strangest, most mysterious constants in the universe. Because while we know how to measure it and how it affects physical processes, we have no idea why it has the value it does. Alpha is a dimensionless constant. That means it has no units, no meters, no seconds, no kilograms. It's just a pure number like pi or e. That's important because it means it's universal. If we met aliens tomorrow, they'd use the same fine structure constant in their physics, even if their units were totally different. But what does it really do? The strength of the electric contact is controlled by alpha. In other words, it tells highly charged objects like protons and electrons how to move toward or away from each other. It also changes how electrons move around in atoms, including how they jump between energy levels, send and receive light, and how close they are to the center. Chemistry doesn't work without alpha. Matter and light don't communicate. Everything that is made up of atoms breaks down. In atomic physics, alpha determines the splitting of spectral lines in hydrogen, known as fine structure, hence the name. In quantum electrodynamics, QED, it shows up in the calculations for how electrons exchange photons and how they interact with the vacuum. In fact, many of the most precisely tested predictions in all of physics, like the anomalous magnetic moment of the electron, rely on knowing the exact value of alpha. But where does it come from? We don't know. Unlike pi, which arises from the geometry of circles, or the gravitational constant g, which relates mass and force in a well-defined way, alpha just exists. It's not derived from a deeper equation. It's not determined by symmetry. It's not a ratio of other constants in any obvious way. It's just measured. We point our instruments at reality and say, well, it looks like 1 divided by 137. It's been bothering scientists for more than 100 years. The great scientist Arthur Eddington was crazy about the letter alpha. He believed it had to come from a deep logical source, something basic about the way the world works. In fact, he tried to figure out what it meant by looking at pure numbers, thinking that 137 was the key to a cosmic code. His ideas never turned out to be true. But people have always been interested in alpha. Richard Feynman once said, "It has been a mystery ever since it was discovered. All good theoretical physicists put this number up on their wall and worry about it." Even today, the fine structure constant remains one of the most precise measured values in all of science, known to better than a part in a billion. And yet, its origin remains completely unexplained. Some physicists have hoped that a future theory of everything might naturally produce alpha from first principles, maybe in string theory, or a quantum gravity framework, or in a deeper unification of forces. But despite decades of work, no such theory has succeeded in deriving the exact value. It just doesn't fall out of the math, at least not yet. Some people have said that alpha could change in different places or times. If that's true, it might help us figure out where it came from. Scientists have studied light from quasars that are billions of light years away to see if alpha was a little different in the past. Some of the data pointed to small changes. Some people saw no change at all. We still don't know. Some people even think that alpha's value is anthropocentric. This means that we wouldn't be here to see it if it were any other way. Atoms might not be steady if alpha were just a little bigger. Stars might not be able to do nuclear fusion right if it were tiny. There may not be a lot of room for life in the world, but we choose to live in it. But again, that's not an explanation. It's an observation about survivorship bias. The mystery of alpha is part of a larger pattern. The constants of nature that define the behavior of everything we observe, yet seem arbitrary. There's the speed of light, the gravitational constant, Planck's constant, and the masses of particles like electrons and quarks. But alpha is especially weird because it ties everything together: quantum theory, electromagnetism, relativity, and still resists explanation. Is gravity built into geometry? Einstein's big leap. In the early 1900s, people thought of gravity like any other force, as a strange force that worked between masses even when they were far apart. In the 1600s, Isaac Newton used math to explain it, but he himself said he didn't understand how it worked. Gravity did something. It made the Earth move toward the sun. It kept apple trees full. No one knew what caused it, though. Einstein's theory of general relativity, published in 1915, reimagined gravity not as a force, but as a result of the shape of space-time. In this view, massive objects don't just pull on each other. Instead, they curve the very fabric of reality, and other objects simply move along that curvature. This was a radical idea. Instead of action at a distance, gravity became a property of geometry. Think of space-time as a rubber sheet. Place a heavy bowling ball in the center, and the sheet sags. Now roll a marble near the bowling ball. It curves toward it, not because there's an invisible force pulling it, but because the path it naturally follows is bent by the sheet. That's the classic analogy for Einstein's view of gravity. But this wasn't just a neat visual metaphor. It produced real testable predictions. General relativity predicted that light would bend near massive objects, that clocks would tick slower in strong gravitational fields, and that space itself would stretch around stars and black holes. Over the past century, these predictions have been tested and confirmed again and again. The 2015 discovery of gravitational waves by LIGO was the latest proof. Ripples in spacetime, created by merging black holes, exactly as Einstein predicted. What does this mean? Does gravity really work? Okay, maybe. General relativity works great for things that are very big, like planets, stars, and the universe itself. It explains things like GPS time changes, the paths of planets, and even how the world is expanding. Things get messy when we get to the quantum level, though. In general relativity, space-time is seen as smooth, continuous, and shaped by mass and energy. This is because it is a classical theory. Quantum physics, on the other hand, says that the world is rough, uncertain, and based on chance. The two ideas don't fit together well. When you use quantum rules to try to explain gravity, you get endless energies, equations that don't work, and other physical nonsense. The biggest problem in physics that hasn't been solved yet is how to explain gravity in terms of the quantum world. Some physicists believe that Einstein's vision was mostly right, but incomplete. That gravity emerges from a deeper quantum framework where space-time isn't smooth, but made of tiny, discrete pieces, like pixels in a video game or atoms in a crystal lattice. In these models, what we see as curvature is the large-scale effect of microscopic interactions. The sheet isn't rubber, it's digital. Others suggest that gravity might emerge not from geometry, but from information. In this view, space-time is built from entanglement, networks of quantum correlations that define what's near and far. Geometry is a byproduct of how information is shared between regions. Gravity becomes an effect of quantum data flow. This isn't just wild speculation. It's supported by work in AID-CFT duality and entropic gravity, where gravity behaves like a thermodynamic force tied to entropy, not geometry. Okay, so Einstein was wrong. Not really. His idea still makes a lot of sense. But it could be like Newton's theory before it, correct, but with some limits. It is clear from Newton's rules how gravity works on Earth. Einstein talks about how things work in space. The next idea could explain how gravity works in the very structure of reality. If gravity is built into space, then why this space? Why do you need 4 dimensions? 3 are space and 1 is time. What makes a curve behave the way it does? Why is gravity not as strong as other forces? Further, what is that something that gravity comes from? These questions aren't just academic. They affect how we understand black holes, the Big Bang, wormholes, and the ultimate fate of the universe. If gravity is geometry, then the universe is a dynamic shape, a living structure that evolves over time. If it's something else entirely, then space-time might be an illusion, just a shadow of deeper laws we haven't yet discovered. Thermodynamic laws, emergent or built-in. The laws of thermodynamics look like easy-to-follow rules at first glance. It's possible for heat to move from hot to cold. Energy stays the same. You can't make a machine that will always work. A big question in physics, though, lies beneath these simple rules. Are these laws really basic, or do they come from more complex statistical behavior? Let's start with the second law, the one everyone remembers. Entropy always increases. In simple terms, it means that systems tend to move from order to disorder. Ice melts, batteries drain, buildings crumble, the universe drifts inexorably toward chaos. The microscopic laws of physics, the ones that govern particles, atoms, and fields, are time-symmetric. That means they don't care whether time runs forward or backward. If you filmed a particle interaction and played it in reverse, the physics would still make sense. The math still checks out. So why, then, does entropy always rise in one direction? The line of time is the name of this game. It's a very strange scientific fact. The world as a whole seems to be stuck in a loop, but everything in the smallest scale can be undone. There are scientists who say the second rule isn't a basic truth. Instead, it's a statistical trend. What happens most of the time when there are a lot of particles? Take a look at a deck of cards. There is only one way for the numbers to be in order, but there are a trillion different ways to mix them up. It's much more likely to get jumbled than neat if you give it enough time. Entropy is that. In this view, the second law is not a cosmic rule. It's just math applied to chaos. It emerges from probability, not principle. The universe isn't forced to become disordered. It just almost always does. This idea of emergence pops up in other areas too. Take temperature. There's no such thing as temperature for a single particle. But when you have billions of them bouncing around, their average energy becomes temperature. Similarly, pressure is just the collective force of countless tiny collisions. So maybe thermodynamic laws, like energy conservation, entropy increase, and heat flow, aren't written into the fabric of the universe. Maybe they just show up when you zoom out. Some physicists believe the second law might be more fundamental than it seems, maybe even more fundamental than time or space. That's because entropy shows up in black hole physics in a big way. In the 1970s, Stephen Hawking discovered that black holes aren't completely black. They emit radiation, now called Hawking radiation. But more importantly, he and Jacob Bekenstein found that black holes have entropy, and that entropy is proportional to the area of the black hole's event horizon, not its volume. It suggested that information about everything that falls into a black hole is somehow stored on its surface, not inside. This led to the famous holographic principle, the idea that the entire universe might work like a hologram, with the physics of a volume encoded on a lower dimensional boundary. And at the center of it, thermodynamics. In fact, some researchers now believe that gravity itself might be an emergent thermodynamic effect. In 2011, physicist Eric Verlinde proposed that gravity isn't a fundamental force at all. It's an entropic force, arising from changes in information and entropy. In this model, objects fall toward each other not because of a mysterious pull, but because that movement increases entropy. If that's true, then thermodynamics isn't just a set of handy kitchen rules. It might be the operating system of the cosmos, the engine from which space, time, and gravity emerge. Which one is it? If Newton's rules tell an apple how to fall from a tree, do they also tell thermodynamics how the world works? What about emergent? Is it a statistical event that only happens when things get big and messy enough? I don't understand the answer, but the question itself is very new. It makes us think about what a physics law really means. Does a rule, like the speed of light or charge conservation, have to be there from the start? If you get to a certain level of complexity, does it only show up when things are really complicated? Laws of physics in the early universe. Did they change? Take a moment to think about the first few seconds after the Big Bang. There were no stars and galaxies in the world. It wasn't even light or atoms. It was a sea of pure energy that was very hot and bubbling. Space and time had just started to form, and the science laws we know today might not have been around at that time. This isn't science fiction. It's one of the deepest, most serious questions in cosmology. Did the laws of physics emerge over time? And if so, were they different in the early universe? We need to talk about unity to understand why this is important. There are four main forces that we understand today: gravity, electromagnetic fields, the strong nuclear force, and the weak nuclear force. However, scientists think that these were not always different. They probably became one force when it got so hot right after the Big Bang that it was impossible to tell them apart. These forces broke apart as the universe grew and shrank, like cracks appearing in metal as it cools. First, gravity stopped working, possibly as early as the Planck time, which is about 10 to the minus 43 seconds after the Big Bang. After about 10 to the minus 36 seconds, the strong force broke apart. Later, the electroweak force, which was made when the weak and electromagnetic forces merged, split in two. This process of force splitting is known as random symmetry breaking, and it's one of the most important ideas in particle physics. If the forces we observe today are the result of broken symmetries, that means the laws that govern them also changed. The equations we used to describe electromagnetism or gravity didn't apply in their current form in the early universe. They only became what they are now after these symmetry-breaking events. So, in a very real sense, the laws of physics were different back then. This shift didn't just affect the forces. It likely affected constants too. Things like the speed of light, the strength of gravity, or the masses of particles might not have been fixed yet. Some theories even propose that constants we take for granted, like the fine structure constant or the gravitational constant, evolved over time, freezing in as the universe cooled. One example of how this idea plays out is the grand unified theory, GUT. In a GUT, the strong, weak, and electromagnetic forces are all aspects of a single force described by one large symmetry group. That symmetry holds at extremely high energy, around 10 to the 16th giga-electron volts, or 1,000,000,000,000 times more energetic than anything we can produce in a lab. Below that energy, the symmetry breaks, and the distinct forces we know today appear. There's also the possibility of phase transitions in the early universe. Just as water freezes into ice, the universe may have undergone sudden shifts, cosmic freezing points, where space itself changed structure. These transitions could have left behind relics, like topological defects or exotic particles. They might even explain why matter exists at all. Inflation, a time of exponential growth that started about 10 to the minus 36 seconds after the Big Bang, is linked to a well-known phase shift. The universe grew faster than the speed of light during this time. Inflation made space smoother, the universe flatter, and it may have caused forces to separate. In addition, it may have locked in some of the universe's early states, such as the values of the rules. And then there's the Higgs field. Today, the Higgs field gives particles their mass. But in the early universe, before symmetry breaking, the Higgs field didn't have a non-zero value. That means all particles were massless. The equations of motion worked very differently. Only after the field settled into its non-zero state did particles gain mass. So again, the laws of physics morphed from one form into another. Why does any of this matter now, billions of years later? Because it shows us that what we think of as universal constants might just be local outcomes, like the weather. Stable now, but shaped by the specific conditions of the early universe. This opens the door to a bigger, bolder idea. What if there are other regions of the universe, or other universes entirely, where the laws are different? In the multiverse scenario, different bubbles of space could undergo different symmetry breakings. Some might have more forces, some might have none, some might not even have space or time as we know it. Our laws would then be environmental, not fundamental, like living in a valley shaped by ice ages long past. Even if we never reach those other regions, we can study the early universe through cosmic background radiation, the afterglow of the Big Bang. Tiny fluctuations in this radiation carry fingerprints of those ancient transitions. By analyzing them, we may one day confirm whether the universe's laws really did evolve. The Higgs mechanism. Why do particles obey mass rules? Mass seems clear to us in everyday life. It's there when you lift a bag. It's clear when a ball hits the ground. And mass is used all over physics, from laws of motion to the study of how gravity works. To add a twist, particles don't have mass when they are born. It's something they get. And the way it works is one of the weirdest and most important things about current physics. The Higgs process is the name of it. Let us go back in time to the 1960s. Physicists were having a hard time with a problem. The standard model of particle physics was correct, but only when some particles had no mass. It didn't work when you tried to add a mass to the equations of the weak nuclear force, which is what makes radioactive matter break down. The W and Z bosons, on the other hand, definitely have mass. A big mass. It is almost 100 times heavier than a proton. How then could that be? How could a theory explain particles that don't have mass, but still work for particles that do? That answer came from a thought that at first seemed very strange. What if space isn't empty? What if it's full of an unseen field that gives particles their mass? The Higgs field is this field that can't be seen. It's everywhere. All of space is filled with it, like a cosmic mud. Strong interactions with this field make particles feel resistance, which makes them gain mass. It doesn't really stop particles that don't interact with it much, like photons, which don't have any mass. This mechanism is remarkably elegant. Instead of having to assign a separate mass value to each particle by hand, the Higgs mechanism lets their mass emerge from how they couple to the field. It's like giving all the dancers in a room different shoes. The floor stays the same, but each dancer moves with different ease depending on their shoes. Mathematically, this idea came with an incredible bonus. It preserved the symmetry of the standard model. You see, in quantum field theory, symmetry isn't just aesthetic, it's protective. It keeps the equations consistent and renormalizable, but adding mass normally breaks that symmetry. The Higgs field, however, allows symmetry to break spontaneously, a subtle twist where the equations stay symmetric, but the solution doesn't. Put a ball on top of a round table and imagine it being balanced. The method is symmetrical in every way. If you push the ball, though, it will roll off in a certain way. In math, the unity is still there, but in real life, things go in a different way. That's breaking balance on its own. The Higgs field works the same way, but the ball is the field value, and the vacuum is where it rests. In 2012, after decades of searching, scientists at CERN's Large Hadron Collider discovered a new particle, the Higgs boson. This was the smoking gun. According to theory, when you disturb the Higgs field, like striking a bell, you get a ripple. That ripple is the Higgs boson, and its mass? About 125 giga-electron-volts, just as predicted. The discovery was a triumph. It confirmed the last missing piece of the standard model. But it also opened up a new mystery. Why this value? Why is the Higgs field's vacuum expectation value the amount it settles at, not 0 or 10 times larger, or infinitesimally small? Why do different particles interact with it in different ways? There's no known reason. The Higgs field just is. Its properties appear finely tuned, almost suspiciously so. This brings us to what physicists call the hierarchy problem. Quantum corrections should blow the Higgs mass up to absurdly high values, far higher than what we observe. To keep it at 125 giga-electron-volts, the universe has to cancel out a massive number of these corrections almost perfectly. That seems unnatural, like someone finely adjusted the dials behind the scenes. A lot of ideas have been put forward to explain this, including supersymmetry, which says that new particles can balance out the quantum corrections. There are extra dimensions that change how fields and gravity work together. Yes, even multiverse models say that we live in one world out of many, and ours has the right Higgs field for life. The strangest option is that the Higgs field might not be basic after all. Some models say it's something that just happens, like sound waves in air or temperature in a gas. Then, the real rules about mass might be deeper in physics, and we don't know about them. Beyond the metaphysics, the Higgs mechanism is also a gateway. It points toward physics beyond the standard model. It suggests that symmetry breaking isn't just about mass. It might be tied to the shape of space, the evolution of the early universe, even the nature of dark energy. Quantum field theory, the code beneath particles. What if electrons, quarks, and photons, which are the tiniest things in the world, aren't really things at all? What if they're just very small waves moving through space-filling fields that we can't see? That is the crazy but important idea behind quantum field theory, or QFT. Physics isn't just a way to do things, it's the operating system that runs everything. To understand how deep this idea goes, we need to zoom out, or rather, zoom in. In classical physics, particles are solid. They have position, momentum, and mass. Like billiard balls, you can track them, bounce them, predict where they'll go. But quantum mechanics shattered that image. Suddenly, particles had wave-like behavior with uncertainties, superpositions, and entanglement. Then, quantum field theory took it even further. QFT tells us that instead of picturing particles as separate dots, each type of particle is an excitation of a quantum field that goes with it. There is a field of electrons, a field of quarks, a field of photons. These fields are everywhere, even in space that seems to be empty. We can find a particle when one of these fields gets excited at a certain point. Picture the calm surface of a lake. That's the field. If you throw a rock in, the water will ripple. The particle is that wave. The thing we call an electron is really just a dot on the electron field below. When you find the particle, you're really measuring a short-lived change in that field that is everywhere. Quantum field theory is the backbone of the standard model of particle physics, the most successful theory we've ever created. It accurately predicts everything from the behavior of subatomic particles to the results of high-energy collisions at CERN. It's why GPS satellites work. It's why nuclear reactors function. It even helps explain how the sun shines. In QFT, forces arise from field interactions. For instance, the electromagnetic force comes from the exchange of virtual photons, temporary blips in the photon field. The strong force that holds protons together, that's mediated by gluons, ripples in the gluon field. The weak force? That's all about the W and Z boson fields. Gravity isn't fully reconciled in this framework yet, but a hypothetical graviton field could one day bridge the gap. The well-known Higgs field we just talked about. Yes, it is also part of QFT. A scalar field interacts with other fields and gives them mass through its all-encompassing impact. This is how the Higgs process works. This point of view is very different. It gets rid of the idea of empty space. A space is never really empty. There are a lot of changing fields, and each one is just below the detecting level. It seems like virtual particles come and go. On the subatomic level, energy jumps around. Sometimes these changes have real effects, like the Casimir effect, which happens when two charged plates in a vacuum are pulled together by quantum field waves. Now you might be wondering, why do we even need this field picture? Why not stick with particles? Because without it, nothing works. Try to describe a particle interaction, like an electron emitting a photon, without quantum fields, and the math falls apart. You get infinities, contradictions, nonsense, but wrap it in the language of fields, and suddenly it all lines up. Every successful quantum prediction we've made, like the electron's magnetic moment or the behavior of the Higgs, comes from QFT. Some of these predictions are accurate to 1 part in a billion. That's like predicting the width of the United States to within the thickness of a human hair. Surprisingly though, we don't understand why QFT works so well. The idea is made up, a type, a tongue we made up. Still, it fits exactly with how things work in reality. That brings up a very troubling question. Is QFT just a tool, or is it the structure of the world itself? Some physicists think it's emergent, that QFT is a low-energy approximation of something even deeper, maybe string theory, or loop quantum gravity, or a purely informational system. Others believe it's fundamental, that the fields themselves are the true stuff of the cosmos, that there are no particles, no objects, just vibrations in the universal fabric. Quantum field theory works beautifully with 3 of the 4 fundamental forces, but gravity, described by general relativity, resists integration. Attempts to combine them, like in quantum gravity or superstring theory, are ongoing but not yet complete. There's also the matter of vacuum energy. According to QFT, empty space should have a colossal amount of energy, enough to rip the universe apart. Yet what we observe via dark energy is tiny. This mismatch is called the cosmological constant problem, and it's one of the biggest unsolved puzzles in physics. Renormalization, fixing infinite equations with finite laws. When scientists looked into quantum field theory's equations for the first time, they found something very scary. It worked until it didn't. Find out how much energy a particle has. On and on. Guess how 2 particles will spread out. On and on. Try to fully represent forces. Once more, infinity. These weren't just rounding errors or simple miscalculations. They were built into the theory itself. Every time a quantum particle interacted with its own field, say, an electron absorbing and re-emitting a photon, the math said the interaction had infinite energy. In physical terms, it was as if even a single particle carried the weight of the entire universe. Clearly, something had to change. Renormalization is one of the smartest and most debated solutions in the history of science. This is how it works. Physicists don't claim that particles live in a vacuum. They know that particles are always buzzing with quantum fluctuations. For instance, an electron doesn't just sit there. A cloud of virtual particles, such as photons, electron-positron pairs, and other short-lived excitations, surrounds it. This cloud changes the nature of the electron. It changes how heavy it is. It changes the charge. But it also adds those results that never end into the calculations. To handle this, physicists apply a mathematical scalpel. First, they admit that the bare values of mass and charge, the raw numbers without any quantum interference, are unknowable. They're not physical. What's physical is what we measure, the electron's actual mass and charge. After all, the quantum noise is included. So we define those measured values and work backwards. At its core, renormalization is this idea that you can get rid of the infinities by changing the definitions of the constants in your theory. The mess is taken away from both sides of the issue. The part of the change that we can see stays the same. Some people thought this was dishonest, especially in the beginning. The great scientist Paul Dirac said it was ugly. Richard Feynman, who helped come up with the idea, once said that it was like hiding dirt under the rug to make it look like the floor is clean. Still, renormalization did its job. No one thought it would work so well. Thanks to renormalization, quantum electrodynamics, QED, became the most accurate physical theory ever devised. Its predictions match experiment to 13 decimal places. That's a level of precision rivaling anything in science. And it wasn't just QED. The technique extended to the electroweak theory, the strong nuclear force, and eventually the full Standard Model. What once looked like a hopeless tangle of infinities became a blueprint for understanding reality. Renormalization isn't just a patch. Over time, it revealed something deeper. Physicists noticed that as you zoom in or out, changing the energy scale of your experiment, the constants in your equations flow. They run with energy. This gave rise to the renormalization group, a framework that explains how physical systems evolve across scales. Imagine boiling water. At the level of molecules, it's chaos, vibrating particles slamming into each other. But zoom out and you see smooth, rolling bubbles. Renormalization tells you how the laws change between those views. It shows why some features disappear at large scales, while others persist. It's a kind of scale symmetry, a law about laws. This concept turned out to be bigger than particle physics. Renormalization showed up in condensed matter physics, statistical mechanics, even critical phenomena like phase transitions. Why do magnets behave like fluids near their melting point? Why does turbulence look like smoke and waterfalls at different scales? Renormalization explains it. Now, some physicists think renormalization might be essential, not just a trick, but a rule in and of itself. A rule that is built into the way the world sets up complexity. It could help us understand why successful field theories work, and why we don't need to worry about high-energy specifics when we're studying low-energy systems, or why our laws seem clear and easy, even though they come from quantum mechanics that isn't. There's a bad side too. It's not possible to renormalize every theory. In other words, that means that some solutions give you infinities that you can't get rid of. For instance, when you try to use QFT to explain gravity, you get results that can't be renormalized. The infinities will always be endless, no matter how you mix the numbers. That's one reason why there is still no solution to the quantum theory of gravity. On a higher level, it means that space and time might need a different structure like strings, loops, or something we haven't thought of yet. Why is time asymmetric, the puzzle of one-way laws? First, let's be clear. Most science rules don't care about time. The math is the same whether you run them forward or backward. A pendulum swinging, two particles crashing into each other, a planet going around the sun. You can play the video backwards and the equations will still not move. This quality is known as time reversal symmetry. From Newton's rules to Maxwell's equations to quantum physics, it's all over the place. We get older. We remember the past, not what will happen next. Even though ice melts, puddles don't freeze over on their own. The smoke rises, but the wood doesn't burn back down. Whole societies rise and fall, but they never go backwards. Time is clearly pointing forward, and we're stuck on it. What's going on? When the rules don't decide which way time goes, why does it feel so different? Yes, entropy is the short answer. The second law of thermodynamics says that in a closed system, entropy, a measure of disorder, can only stay the same or increase. That's it. That's the whole rule. And yet, it's the most powerful explanation we have for time's one-way street. Entropy gives time direction. It's why your coffee cools instead of heating up on its own. It's why scrambled eggs don't unscramble. And it's why the universe is moving from a state of low entropy, early cosmos, to high entropy, eventual heat death. But this brings up a scary question. Why was the world so well organized to begin with? Not only was the Big Bang hot and thick, but its entropy level was also very low, a smooth, featureless area with only a few gravity bumps. That's the same as putting all the puzzle parts in a box and finding them put together already. This does not make sense, and chaos can only go up from there. That is the direction of time in thermodynamics, the one we sense. Some physicists argue this initial condition, this past hypothesis, isn't something you can explain. It's just the way things started. Others think it might be a statistical fluke or the result of a deeper law we haven't discovered yet. There's also the psychological arrow, our experience of memory, cause and effect, and anticipation. We remember yesterday, not tomorrow. We can plan ahead, but not backward. And this seems to align with entropy. Memory formation increases entropy. Brains are thermodynamic machines, after all. Then there's the cosmological arrow, the fact that the universe is expanding. Space itself is stretching, dragging time along with it. Could this expansion define a preferred direction? Some theories say yes, especially if the universe eventually contracts again. Time's arrow might reverse, though we'd never notice, since our memories and processes would reverse too. And what about quantum physics? The Schrödinger equation, the foundation of quantum mechanics, is time symmetric. But measurement isn't. When you observe a quantum system, the wave function collapses. Possibilities vanish. Outcomes get locked in. This collapse seems to introduce irreversibility, but whether that's real or just a byproduct of our limited perspective is still debated. The idea of quantum decoherence is also very interesting. It's easy to say that quantum systems get messy when they interact with their surroundings. When particles become entangled, they lose their superpositions and behave in a more normal way. Decoherence isn't exactly permanent, but in real life it is. It only goes one way, the same as entropy. In particle physics, there's even a tiny crack in the wall of time symmetry. Experiments with K-mesons, kaons, show slight violations of CP symmetry, charge, and parity. And according to the CPT theorem, if you violate CP, you must also violate time reversal symmetry. That's right. In very specific quantum conditions, nature seems to prefer a direction in time. It's not much, but it's real. Some physicists believe the answer lies not in the equations, but in boundary conditions, that the laws are symmetric, but the universe isn't. The stage is set asymmetrically, and everything that follows plays out with a forward rhythm. Others believe that time itself is emergent, something that arises from entanglement or thermodynamic gradients or the expansion of space. In that view, there's no deep mystery. Time isn't fundamental at all. Universality. Why unrelated systems follow the same laws. What is the link between neural networks, the stock market, magnets close to their critical points, and hot water? At first look, there is nothing there. Physics, materials science, finance, and biology are all very different fields from these systems. Interestingly, though, they often act in ways that are mathematically the same. The thought that very different systems can follow the same rules when they get close to certain critical spots is what universality is all about. Take a container of water. As you heat it toward its boiling point, something strange happens. Fluctuations in temperature, density, and structure begin to occur at every scale. Tiny clusters of vapor form, collapse, reform, blurring the line between liquid and gas. This is called critical behavior, and it's not just messy, it's mathematically rich. Now replace the water with a magnet. Cool it toward the Curie temperature, the point where magnetic alignment breaks down. Again, you'll see similar behavior. Domains of aligned spins fluctuate, grow, and vanish. The system becomes unpredictable on a small scale, but highly structured statistically. When scientists plot the behavior of both systems near their respective critical points, like how fluctuations scale with size or time, they get the same equations, the same graphs, the same exponents. Despite involving different particles, forces, and scales, these systems act the same. They belong to the same universality class. Universality classes are defined by a few key properties. The dimensionality of the system, is it 1D, 2D, 3D, the symmetries involved, and the range of interactions. Details like the exact materials, molecules, or microscopic mechanisms don't matter. As long as two systems share these core features, they'll behave the same near criticality. What is the link between neural networks, the stock market, magnets close to their critical points, and hot water? At first look, there is nothing there. Physics, materials, science, finance, and biology are all very different fields from these systems. Interestingly, though, they often act in ways that are mathematically the same. The thought that very different systems can follow the same rules when they get close to certain critical spots is what universality is all about. So where does this balance come from? Scale invariance is one reason for this. As systems get close to critical points, they lose their sense of exact size. The changes look the same whether you zoom in or out. This is known as self-similarity, and it's the reason why important systems have fractals. When equations don't care about how big the thing they describe is, they tend to break into forms that are the same for everything. Another part comes from Kenneth Wilson's renormalization group theory, which he came up with in the 1970s. It showed step by step how systems change as you zoom out or see them at a larger size. Smaller details become less noticeable as you do this. The fine roughness goes away, and the broad shape takes over, like when you carve with clay. At their tipping points, Different materials act the same way because of this. The small details don't matter. But universality isn't limited to physical systems. In biology, neural networks sometimes show critical behavior, balancing between order and chaos to maximize processing power. In geology, earthquakes follow power laws similar to those of phase transitions. In sociology, crowds, traffic jams, and viral trends on social media often display critical dynamics. They're not made of atoms, but they still boil over. This hints at something deeper. Maybe the universe has a limited menu of behaviors, like how all songs, no matter the genre, are built from the same musical scales. The ingredients vary, but the rules of composition stay the same. Why does the universe allow for universality at all? Why should vastly different phenomena share mathematical behavior? Some scientists think this is a feature of emergence, that when complex patterns arise from simple rules, they converge on a few robust outcomes. Others suspect there may be underlying symmetries baked into the fabric of space, time, or computation itself. A crazy thought? That unity shows that there is a computational world where systems behave similarly because they have the same code, no matter how they look. It's like having different apps that use the same OS. Quantum entanglement. Are laws non-local? Think about two particles. They are both born at the same time in a quantum event, like when a tiny particle breaks apart, and then they fly apart across the universe. One goes left, that one on the right. Years go by, even light years away. You are now going to measure one of them. You know something about the other person right away, faster than any signal could travel. Not just a guess, it's not likely. Truth, no matter how far away. At first glance, this sounds like magic, but it's not fiction, it's not theory. This is a real, testable, observable phenomenon at the heart of quantum mechanics. And it challenges one of the deepest assumptions of physics: locality. The idea that objects are only influenced by things in their immediate surroundings. Locality has always been a foundation of science. From Newton to Einstein, the rule has been clear. No influence can travel faster than light. You want to affect something across the universe? Send a beam, send a force, send a signal. But entanglement doesn't play by those rules. It seems to allow instantaneous influence between distant objects with no signal at all. In quantum mechanics, particles are described by wave functions, mathematical descriptions of all possible states they could be in. When two particles become entangled, their wave functions intertwine. Even after separation, they must be treated as a single system. This means measuring one particle doesn't just tell you about it. It collapses the entire wave function, instantly updating the state of the other particle. Einstein was known to have hated this idea. He said it was spooky action at a distance, and said it had to be a trick. He suggested that the particles might have had secret information, hidden variables, from the start that decided what would happen. This would keep the clean classical view of the world and keep location the same. Physicist John Bell came up with a mathematical inequality in the 1960s that tested the idea that hidden variables might be able to explain entanglement. Scientists used Bell's inequality to do tests decades later and found that linked particles don't follow it. Quantum predictions were right on the money, but local hidden variable ideas were wrong. That is, quantum entanglement is real, but proximity isn't, at least not in the traditional sense. This doesn't mean that it's possible to talk faster than light. That is still against quantum theory because it would break the chain of events. Twirling cannot be used to send a message, but the fact that real-time knowledge about one particle relies on what happens to another particle says that some physics laws are not limited to one place. So what does that mean for the structure of the universe? It could mean that space and distance are illusions, or at least not as fundamental as we thought. If two particles light years apart can behave as one system, then the fabric of space-time may be stitched together not by geometry, but by quantum information. This idea gets support from theories like the ER=sign EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. It suggests that entangled particles are connected by microscopic wormholes, Einstein-Rosen bridges, that preserve non-locality in a geometric way. If true, this would mean that entanglement and space-time geometry are two sides of the same coin. Even more radically, some researchers argue that space itself is built from entanglement, that the shape of the universe emerges from quantum information networks, like a giant cosmic web, where particles are more or less near, depending on how entangled they are, not how far they are in physical distance. Entanglement is already being used in quantum computing and quantum cryptography. It's the reason quantum computers can process multiple possibilities at once. It's why quantum encryption is theoretically unbreakable, because any attempt to eavesdrop destroys the entanglement. Entanglement forces us to abandon the idea of separateness. In the quantum world, nothing is truly isolated. Every particle is part of a broader system. Every measurement is a relationship. Reality is not made of parts, it's made of connections. Dark matter and dark energy, do they obey our laws? There is one thing that the universe keeps teaching us. Most of what is real is unseen, and we don't fully understand it. It's thought that about 95% of the universe is made up of things other than atoms and light. About 27% of it is dark matter. Dark energy makes up an even bigger part, about 68%. That only leaves 5% for all the things we've directly studied, like people, coffee, stars, planets, and quantum tests. Now for the scary question. Do dark matter and dark energy follow the same rules of physics that we do? Or do they follow a totally different set of rules that we haven't found out about yet? Let's start with dark matter. It's called dark, not because it's evil or spooky, but because it doesn't emit, reflect, or absorb light. We can't see it. We only know it's there because of gravity. Galaxies spin faster than they should. Clusters of galaxies bend light from behind them more than expected. Without something extra, something invisible, these motions make no sense. That something is dark matter. What is it, though? That's a question we've had for decades. Most people think that dark matter is a particle, which is something big, slow, and not very likely to interact with other things. There is even a name for these made-up particles, WIMPs, which stands for Weakly Interacting Massive Particles. Theories outside of the standard model, like supersymmetry, were able to predict them. Physicists have dug up huge devices to try to catch dark matter particles interacting with normal matter. Crystals that are very cold, tanks that hold liquid xenon, and even the Large Hadron Collider have been used. So far, nothing. There was not a single proven discovery. There is no sound at all. There are other candidates too, like axions, ultralight particles that could be swarming the universe as a kind of cosmic fog, or even primordial black holes, leftover relics from the Big Bang. Still, no direct hits. Even if we found a dark matter particle, we'd still have to ask, why does it obey gravity but not electromagnetism? Why doesn't it interact with the strong or weak nuclear forces in detectable ways? Is it simply blind to those interactions? Or does it follow an entirely different version of physics? Some physicists believe dark matter may have its own forces, its own symmetries, its own dark electromagnetism. In that view, our visible universe is just one part of a broader cosmic ecosystem, like a reef only partially lit by sunlight, with a whole world hidden in the shadows. There's also dark energy. Dark energy is different from dark matter in that it pushes the world apart instead of pulling it together. It is the force that is making space expand faster. Dark energy wasn't just a shock when it was found in the late 1990s by looking at supernovae far away. It was a change. Before that, we thought the growth of the world might slow down. Instead, it's getting faster. What, though, is dark energy made of? Some ideas say it's just the cosmological constant, which is Einstein's equation for the set energy density of empty space. Some people think it's a field that changes over time, like the Higgs. Some people think it might even be proof that general relativity doesn't work on big scales and needs to be rewritten from scratch. We still want to know if dark energy works the same way as regular matter. Do they have a game we don't know about? If dark energy is the unstable changes of quantum fields, then why does its number not match what theory says it should be? As we've already said, quantum field theory says that the quantity of energy in the void will be much higher than what we see as dark energy. That gap, which is more than 100 orders of magnitude, is the biggest mistake in current physics theory, which raises the possibility that dark energy doesn't arise from known quantum fields at all. Maybe it comes from an unknown sector, what some call a dark sector, with its own particles, laws, and constants. So what's being done to solve this? Astronomers are launching new missions to study the universe's expansion with extreme precision. The Euclid telescope, launched by the European Space Agency, and NASA's upcoming Nancy Grace Roman Space Telescope, are both designed to map the cosmos and measure dark energy's influence on galaxies across time. If dark energy evolves, even slightly, we might catch it in the act. Meanwhile, physicists continue refining modified gravity theories, ideas that tweak Einstein's equations instead of adding mysterious energy. Some of these suggest that the laws of gravity themselves are incomplete and need a broader framework. Unitarity. Why can't information be lost? In quantum physics, one of the weirdest and most important rules is that you can't delete information. The universe should be able to figure out how every quantum event happened, even if there are explosions, black holes, or crashes between galaxies. Unitarity is the name of this idea, and it is at the heart of how quantum theory explains reality. The problem is that the more we look into it, the more this rule seems to go against what we see. There are some really big puzzles in physics that come from this stress, especially when it comes to black holes. Let's break it down. In quantum mechanics, the evolution of a system is described by the Schrödinger equation. This equation is unitary, meaning that if you start with a quantum state and let it evolve, the total probability remains exactly 1. Nothing leaks out, nothing is lost. Mathematically, this guarantees that if you reverse time, the system would retrace its steps perfectly. That might sound abstract, but the implications are massive. It means that quantum reality is fundamentally reversible. You might not have the computing power or knowledge to reverse a scrambled egg, but the universe, in theory, can. So why does this matter? Because classical physics often allows for loss. A drop of ink dissolves into water and becomes unrecoverable. A burned book becomes ash and smoke. But those are thermodynamic processes, statistical, not fundamental. Deep down, if we had perfect information about every atom and photon, we could reconstruct the book. In the 1970s, Stephen Hawking showed that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon, what we now call Hawking radiation. Over time, this causes the black hole to evaporate. But here's the problem. That radiation appears thermal, meaning it carries no information about what fell in. Let's say you throw a dictionary into a black hole. The black hole goes away. The radiation doesn't give away anything about what's in the book. That's loss of information, which is a direct violation of unitarity. The black hole information paradox is one of the most important arguments in current physics because of this. Some physicists argued that unitarity must break down, that black holes represent a fundamental exception to the rule. Others, including Hawking later in life, reversed course and proposed that information must somehow be preserved, possibly encoded in the Hawking radiation through subtle quantum correlations. Still others have suggested the answer lies in quantum gravity, a theory that we don't fully have yet. Perhaps when space-time is quantized, these paradoxes resolve. Or maybe the information is stored on the event horizon, in line with the holographic principle, the idea that all information inside a volume of space is encoded on its boundary. That last idea, holography, gained traction through the work of physicists like Juan Maldacena, whose ADES-CFT correspondence showed that a gravitational system in one dimension can be fully described by a quantum system on its lower dimensional boundary. This suggests that black hole evaporation might be unitary after all, just in a form we don't yet understand. And there's another twist. In 2019, calculations using a concept called the island rule showed that if you treat black hole radiation carefully enough using quantum entanglement and replica wormholes, the resulting information content does appear to be preserved. These were the first real signs that unitarity might be saved, even in black holes. There's more to unitarity than black holes. It's a general rule that all quantum computing, interference patterns, and entanglement effects are based on. If it doesn't work, our whole way of expecting and describing quantum events will not work either. It also changes how the arrow of time works. Time only seems to go in one way if the world can go backwards. The answer lies in entropy, which is the statistical behavior of big systems. But unitarity makes sure that this flow, that seems to go only in one direction, doesn't break any quantum rules. Even quantum measurement, with its seemingly irreversible collapse of the wave function, may not truly break unitarity. In interpretations like many worlds, all possible outcomes still exist. The universe just branches into different paths. Information isn't lost, it's distributed. And in the cutting edge of theory, there are even deeper questions. Could unitarity itself be emergent? Could it arise from a more fundamental probabilistic process? Or is it a strict rule built into the core of all existence? There are potential cracks in unitarity that can let information leak and make predictions impossible. If unitarity fails even a little, this can happen. That would mean it's possible to copy quantum bits, quantum encryption would break, and the very foundations of computing would no longer be reliable. But so far, every effort to measure quantum systems, all the way down to single particles in labs by themselves, has shown that they are unitary. There are times when the world isn't fair, kind, or clear, but it is very reliable. Constants that vary? Searching for shifting laws. We don't think much about physics constants, which are numbers that don't change and describe how the world works. Everything from the speed of light to the charge of an electron. These are not just numbers on a math test. They are the knobs that make reality possible. What if they're not really steady, though? The idea seems absurd at first. After all, the term constant implies unchanging. But some physicists and cosmologists have begun to explore a bold possibility, that certain constants may have shifted over the history of the universe, or could vary across vast distances in space. And if that's true, then the laws of physics as we know them aren't really universal. They're local rules, ones that might look different in another corner of the cosmos, or even a different epoch of time. The fine structure constant, often symbolized by alpha. This number, approximately 1/137th, determines how strongly light and matter interact. It shapes the structure of atoms, chemical reactions, and the way stars burn. It's a ratio involving the elementary charge, Planck's constant, the speed of light, and the vacuum permittivity. In short, it touches everything. Some research on the light from quasars, which are very far away stars that were beacons billions of years ago, suggests that alpha may have been a little different in the past. Not by a huge amount, but by a few parts per million. In science, though, even that small shake is called a seismic event. It would mean that the strength of electromagnetism has changed over the course of space-time. Other constants under scrutiny include G, the gravitational constant, which determines the strength of gravity between masses. Unlike electromagnetism, gravity is incredibly weak, but also infinite in range. It binds galaxies, bends light, and shapes the expansion of the universe. If G has shifted even slightly since the early universe, it would affect everything from the size of stars to the rate of cosmic inflation. There's also C, the speed of light in vacuum. Currently pegged at 299,792,458 meters per second, it serves as a cosmic speed limit. But what if, early in the universe's history, light traveled faster? Some variations of the varying speed of light, VSL theory, suggest that a higher value of C in the early universe could explain why the cosmos is so smooth and homogeneous, offering an alternative to inflationary theory. Then there's the proton to electron mass ratio, another constant that affects atomic structure and chemistry. Some observations of spectral lines from distant galaxies suggest that this ratio may have experienced a tiny shift over the past 12 billion years. Again, the evidence is controversial, but it's enough to spark investigation. These thoughts are not just wild guesses. They naturally come from a number of theoretical theories, especially those that deal with extra dimensions, string theory, and cosmic scalar fields. In some types of string theory, for example, the things we think of as constants are really the shape and arrangement of dimensions that are curled up. Even if the changes are small, the constants can move if the settings do. Scalar fields, like the ones that have been suggested for dark energy, can also couple to matter in ways that change constants. Imagine a background field that goes all the way across the universe and slowly rolls or oscillates, changing the values of important factors as it goes. Constants aren't fixed in this picture. They're more like heaters that are set by the conditions in space. No constant has yet been proven to vary. Most results are within error margins or suffer from conflicting data. But the hunt continues, with better telescopes, more precise atomic clocks, and improved models of the early universe. Atomic clocks, in particular, have reached extraordinary levels of precision. Experiments comparing clocks at different altitudes, locations, or orientations relative to gravitational fields are sensitive enough to detect the tiniest variations in timekeeping that might hint at deeper changes in constants. So, what would it mean if a constant really does vary? First, it would force us to rethink what a physical law really is. Are laws fixed, timeless truths, or are they just descriptions of the universe right now? If constants evolve, then maybe so do laws. Physics might not be a static structure. It might be alive, shaped by deeper dynamics that we don't yet understand. It also opens the door to the multiverse idea. In some models, different regions of a larger multiverse could have different constants, essentially running on slightly altered physics. Maybe only a small fraction of those universes can support stable matter, complex chemistry, or life. That's where the anthropic principle comes in. Perhaps we observe these specific constants, not because they're uniquely right, but because we couldn't exist to notice them otherwise. Is the universe a simulation? The pixelation test. It sounds like something out of science fiction, or even worse, a late-night Reddit post. But some of the smartest people in science and philosophy are really thinking about the idea. What if the whole world is just a computer game? Not figuratively, but really. That everything we see, feel, and measure is part of a world that was made by computers and is very powerful. This idea isn't new. It echoes ancient philosophical thought, Plato's cave, Descartes' evil demon, or even the Hindu concept of Maya, the illusion of the material world. But the modern version comes with digital teeth. It was catapulted into scientific discussion in 2003 when philosopher Nick Bostrom published a paper proposing that one of three things must be true. 1. Humanity will go extinct before becoming technologically advanced enough to run universe-scale simulations. 2. Advanced civilizations will lose interest in running simulations. Or 3. We're almost certainly living in one. Let's talk about the idea of pixelation. Without a doubt, every game is built on a grid, a ceiling on sharpness. Some quantum gravity theories also say that the world may have a basic limit, which is called the Planck length. It is equal to about 1.6 times 10 to the power of negative blank meters dot rate chunks, like the dots on a screen. If this is true, it would make reality reach a certain level of clarity. Our equations already give us hints of these limits. The Heisenberg uncertainty principle limits how well we can figure out where a particle is and how fast it is moving in quantum physics. In special relativity, nothing can move faster than light, which means that there is a maximum rate at which information can be updated. It sounds like a cap on processing, doesn't it? Even stranger are things like quantum coupling, which makes it seem like particles can quickly talk to each other over very long distances. In a made-up world, this might be seen as a database update, since the system changes the states of both particles at the same time, which isn't possible in real reality. Some researchers have proposed concrete ways to test the simulation idea. One line of inquiry involves anisotropies in cosmic rays. If the universe is rendered on a computational grid, ultra-high energy particles might subtly interact with that grid, creating preferred directions or interference patterns, like jagged edges on a digital model. Another angle is holographic noise, a kind of pixel-level jitter in spacetime that could be detectable with next-gen interferometers. But let's pause and be clear. There's no evidence yet that we live in a simulation. These are just testable consequences if we do. The universe might just happen to have properties, like Planck limits and entanglement, that also happen to resemble computation. No matter, let's think about the idea. It looks like a game. Who or what is running it? As Bostrom first suggested, it could be a powerful alien society running simulations of ancestors. Or it could be a cosmic AI that isn't based on biology at all, playing with physics engines for fun or study. Even stranger, it might not be an outside being at all. It's possible that the model is us going back in time. Consciousness plays a role in itself. What about glitches? Are déjà vu, Mandela effects, or UFOs examples of a rendering error or patch update? Probably not. But even asking that question is telling. It shows how deeply this idea has embedded itself in our collective imagination. Suppose we do confirm that our universe is a simulation. Does that change anything? The physics still works. The planets still orbit. The laws still apply. Just because Mario is simulated doesn't mean gravity doesn't affect him in-game. The real question becomes, what level of the stack are we on? Are we first-generation Sims, or do we live in a simulation of a simulation? Some scientists argue that even if we can never prove it, simulation theory is useful because it forces us to re-express physical laws in computational language. Quantum field theory, for example, is already structured like a code base. Fields are like data structures. Particles are excitations. Feynman diagrams resemble network transactions. Maybe this is just the most natural way to describe a computational universe. Also, remember that modeling does not mean fake. It could just mean made by rules. There is still growth in a fake forest. A mind that isn't real still thinks. What you remember about your life, your love, and the way it felt would all still be real to you. But there's a more important question. Is this exercise being watched if it is real? Is there someone or something watching over cosmic events, like how we watch our video game characters? Is there a way to turn it off, a way out? What would happen if the system saw you trying to break the rules? We might not be being watched, though. It's possible that we're stuck in a cold, automatic loop, a game that its author has given up on for a long time. Then we're free. Feel free to look around, question what you think you know, and find the edges of the code, if there are any. There's a term in computing called emergent behavior. It's when simple rules give rise to surprising complexity. If the universe is simulated, perhaps we are that emergence. Self-aware, unpredictable, ungoverned by the intentions of the original coder. That's either terrifying or exhilarating. Broken symmetries when laws fail on purpose. At first glance, symmetry looks like the most important thing in all of physics. Things with more symmetry tend to have rules that are easier to understand, more beautiful, and more general. Everything in nature is symmetrical, from the way a snowflake is balanced to the rules that tell particles how to interact with each other. But perfection isn't important in the world below the atomic level, because the universe does some of its most important things only when balance is broken. In physics, a symmetry refers to a transformation that leaves the system unchanged. Rotate a sphere, same sphere. Reflect an equation across a mirror, same outcome. These operations, when valid, often signal deep truths about conservation. Time symmetry, That leads to energy conservation. Space symmetry, momentum is conserved. These connections come from Noether's theorem, one of the most powerful tools in theoretical physics. So when a symmetry breaks, we'd expect disorder, chaos, laws falling apart. But what we actually find is something far more fascinating. New laws emerge, new particles appear, forces differentiate, universes unfold. Take the early universe. Right after the Big Bang, physicists believe all fundamental forces were unified. One elegant, high-energy superforce governed the cosmos. But as the universe expanded and cooled, this symmetry shattered. Like water freezing into ice, the uniform force split into separate domains: gravity, the strong force, the weak force, and electromagnetism. This event is known as spontaneous symmetry breaking. Imagine that the point of a pencil is perfectly balanced on its back. It might fall anywhere. When it does tip, though, it goes in a certain way. The chosen direction breaks the original symmetry of rotation. But that break makes structure. Everything else did the same thing. And that tip, in the beginning of the universe, changed everything. In the world of broken symmetry, the Higgs process is one of the most well-known cases. The Higgs field flows through space like mud that you can't see. Some particles gain mass more strongly than others when they interact with it. But there's a catch. The field itself breaks one of the most basic rules of the Standard Model. It makes the playing field less level. The W and Z bosons have masses because of this unevenness. This makes the weak force short range, while the photon has no mass and long range. So ironically, breaking symmetry gave our universe shape, weight, and complexity. Without it, everything might move at light speed. No atoms, no chemistry, no biology, just sterile, featureless energy. But broken symmetry doesn't only show up in grand cosmic events, it's hiding in your refrigerator. Look at a magnet. When it's heated above a certain temperature, the magnetic field disappears. The atoms stop pointing in the same direction. Symmetry is restored. Cool it down again, they realign. The magnet becomes ordered once more, but only by choosing a direction. That choice? Another symmetry break. This kind of transition, where phases of matter shift based on temperature or energy, is a universal phenomenon, and it gives physicists a powerful analogy to study how the early universe behaved. That's why condensed matter physicists and cosmologists often speak the same language. But symmetry breaking isn't always spontaneous. Sometimes it's subtle and baked into the math itself. A famous example? CP violation. That stands for charge and parity violation, where particles behave differently from their mirror image antiparticles. In theory, matter and antimatter should have annihilated each other after the Big Bang. Yet here we are, made of matter. CP violation is one of the few known mechanisms that can explain this imbalance, but it's rare. Only certain particles, like neutral kaons and B mesons, have shown this violation in experiments. Still, it's enough to suggest that symmetry had to be broken for anything to exist at all. Some string theory models propose that our universe's symmetries are just remnants, shattered echoes of a more perfect, higher dimensional reality. In those early dimensions, everything was symmetric and whole. As the dimensions collapsed or compactified, the symmetries broke like shattered glass. We now live among the fragments. All of this leads to a strange idea. Symmetry isn't always a good thing. It's sometimes the lack of balance that makes everything else make sense. Think about living. In a chiral and uneven design, DNA swirls. The left side is where our hearts are. Both sides of our brains do different things. If nature had absolute uniformity, there would be perfect clones. Nature, on the other hand, picks structure over beauty and complexity over balance. What does this mean for the rules of physics? Apology in physics when geometry enforces behavior. What if the laws of physics didn't come from forces, particles, or fields, but from the very shape of space itself? That's the strange and beautiful territory of topology in physics, where the geometry of space, not what's inside it, starts calling the shots. To understand this, we need to make a sharp distinction. Geometry is about distances and angles, how big, how far, how curved. Topology, on the other hand, is more abstract. It cares about what stays the same when you squish, stretch, or twist space without tearing it. A coffee mug and a donut. Topologically identical, they both have one whole, but a sphere and a pretzel? Totally different. In this hypothetical world, particles don't act in a certain way because of a force pressing on them, but because that's how space is shaped. That's how powerful topology is in physics. Let's start simple, with topological insulators in condensed matter physics. These are materials that don't conduct electricity through their bulk, but have surfaces that conduct perfectly. What's wild is that these conducting states aren't caused by ordinary forces. They're protected by the material's topological structure. You can deform the system all you want, add imperfections, impurities, noise, and the behavior doesn't change. It's robust, because topology doesn't care about small tweaks. This idea has taken the physics world by storm. In the last decade, topological phases of matter have become a new frontier, not because of what the materials are made of, but because of how quantum states are arranged across them. The shape of the quantum wave function, how it wraps and winds across space, creates rules that are unbreakable. Now zoom out from electrons and materials and think cosmically. Topology shows up in field theory and string theory, where particles are no longer point-like, but extended objects, like strings, loops, or membranes. The way these objects wind around each other can create physical consequences. A string wrapped around a dimension can't just disappear, it's stuck. That winding number is a topological quantity, and it defines what kind of particle you get. In gauge theory, too, the kind that governs the standard model, certain configurations of fields can't be smoothed away. These are called instantons or monopoles. They're not solutions you can gradually deform into nothing. They're topologically protected, and that protection leads to real phenomena: quantized charges, magnetic flux, particle statistics. One of the most fascinating outcomes of topology in physics is the Aharonov-Bohm effect. Imagine an electron traveling around a magnetic field. The field is confined to a region the electron never touches. Classically, nothing should happen, but quantum mechanics says otherwise. The electron's wave function senses the topology of the field's presence, even at a distance, and it shifts phase. That shift is measurable. That's topology, writing laws with invisible ink. Topology also shows up in quantum computing. Some of the most promising quantum bits, called anyones, exist only in two-dimensional spaces with exotic topologies. When you braid anyones around each other, they change the state of the system in ways that can't be undone by noise or measurement. That's why topological qubits are so powerful. They're error-resistant, not because of better hardware, but because of the deep geometry of how information is stored. Even in cosmology, topology could be the architect behind strange cosmic behaviors. There's a chance the universe itself is not infinite, but wraps around on itself in some complex, twisted shape. If so, light from distant galaxies could loop back to us, producing repeating patterns in the cosmic microwave background. It's like living inside a cosmic video game map, where walking far enough in one direction brings you back to where you started. Physicists have scoured the sky looking for these repeating patterns, circles in the CMB, strange alignments of galaxies. So far, no smoking gun. But the possibility that our universe has a non-trivial topology is still on the table. And then there's the topological censorship conjecture in general relativity. It basically says, if crazy topologies exist, like wormholes or time loops, they have to be hidden behind event horizons. You can't just fly a spaceship through a shortcut in space. The laws of physics enforce a kind of censorship. They protect causality by locking bizarre geometry behind cosmic firewalls. So, what does it all matter? Because it makes us think about what a law really is. Rules are what most people think of when they hear the words laws or laws of conservation of energy. But in a topological world, some things will happen no matter what. They're not rules. Not because someone or something tells particles what to do, but because of how space is set up, they have no choice. Does space-time quantize at the Planck scale? If you keep moving in, past atoms, quarks and strings, space might not be smooth anymore at a certain point. This is the Planck scale, which goes from about 10 to minus 35 meters. It's smaller than anything we've ever seen. It could be the key to everything, though. Scientists have long thought that space-time isn't infinitely divided, that once you go past a certain point, you can't cut space or time any smaller, because reality is made up of separate pieces. They are like dots on a screen, but they are for space. This is the idea behind quantizing space and time. This would change everything if it were true. Let's start by taking the scale apart. From the speed of light, Planck's constant, and the gravity constant, we can figure out the Planck length, Planck time, and Planck mass. These aren't just random. They are what happen when you combine quantum physics, relativity, and gravity into one body. Planck time is the shortest meaningful unit of time, about 10 to the minus 44 seconds. Try measuring anything smaller than that, and quantum fluctuations of gravity swamp everything. You wouldn't just be observing a particle, you'd be probing the jittery foam of space itself. So what does this foam look like? Theorists have proposed several models. One is loop quantum gravity, where space is woven from loops, tiny, discrete bits of volume. Each loop is a quantum of area or volume like a Lego block. These loops form networks, and the geometry of space emerges from how they connect. The closer you zoom, the more you see this scaffolding. In causal set theory, space-time is a collection of points ordered by cause and effect. There's no background space, only events and the relationships between them. Space-time grows like a tree, with each new node linked by causality. Here, distance and geometry are secondary. The order of events is what really matters. In string theory, the quantization isn't of space itself, but of the vibrations of strings. But even here, the theory implies a minimal length. You can't probe below the string scale without hitting paradoxes, because your measuring device would collapse into a black hole. If space-time really is quantized, it means there's no such thing as a perfect point or an exact instant. Every position is fuzzy. Every event is smeared. The smooth curves of Einstein's general relativity would give way to jagged edges and discrete patches. It's not just a math trick, though. There would be effects on the body. One thing is that quantum gravity would finally make sense. Our best ideas, general relativity and quantum field theory, don't work together right now. One is based on chance and doubt. Another one is about smooth shapes and geometry that doesn't change. But space-time might work like a bridge if it is made up of separate parts. The quantum jumps of particles and the bending of space by gravity would finally agree on something. Take the black hole information paradox. If space is continuous, then Hawking radiation seems to lose information. But if space is pixelated, every bit of area on the event horizon could encode a quantum of information. This is the idea behind the holographic principle, that all the information inside a region can be encoded on its surface. It might also explain the cosmological constant problem. Quantum field theory predicts a vacuum energy that's absurdly huge, so big the universe should have torn itself apart long ago. But if the vacuum has a discrete structure, maybe its energy is stored in ways we don't understand. Maybe the vacuum isn't empty, it's loaded with microscopic structure. How are we going to test this? It's not simple. Effects on the Planck scale are very small. We are not able to make a lens that little. At those energies, we can't even crash particles into each other yet. But there are hints. Some scientists are looking for changes in high-energy cosmic rays, tiny outliers that might point to graininess deeper down. Others are looking for echoes in gravitational wave data that could show quantum changes in spacetime. Tabletop studies, such as holometer interferometers, are also used to find jitter in the positions of mirrors that could be caused by Planck scale noise. If space is broken up into pixels, you might see a small, steady blurring in where things are, even when there is nothing there. If the universe is pixelated, is it being simulated? Not necessarily, but it does mean reality has a resolution limit. Like any good video game, there's a grid behind the graphics. That grid isn't metaphorical, it's what reality is made of. Cosmic inflation, Did laws expand with space? Everything in the world did something crazy in the very first seconds after the Big Bang. It got bigger, not over time. It's not nice, but very quickly. In an instant, space itself grew by an unthinkable amount, maybe even 10 times the power of 78. The event in question is known as cosmic inflation, and it may have done more than change the size of the universe. It may have also created the rules that control it. In the 1970s and 1980s, physicists faced a few cosmic puzzles. First, the horizon problem. Regions of the universe billions of light years apart have the same temperature, even though there's no way light, or heat, could have traveled between them since the Big Bang. That kind of uniformity shouldn't be possible. Second, the flatness problem. The universe appears to be geometrically flat, like a stretched out sheet, but that's an unstable situation. Any tiny curvature early on should have amplified wildly, yet it didn't. Inflation solves both. It proposes that less than 10 to the power of minus 36 seconds after the Big Bang, the universe underwent exponential expansion. It was driven by a hypothetical field called the inflaton, which dominated the energy of the cosmos. Like a ball rolling slowly down a hill, this field kept space expanding at a breakneck pace, smoothing out irregularities and diluting any curvature. What if inflation did more than smooth out space? Could it have also been locked in the laws? Take a look. There is a good chance that the inflaton field affected how forces and particles formed, since it set the universe's energy, temperature, and structure. Gravity, electromagnetism, the strong force, and the weak force are the 4 basic forces. The symmetry breaking that split them may have been frozen in during the inflationary epoch. That is, cosmic expansion did more than just change where the universe is. It might have said how to do it. The field of physics is now looking into whether inflation smoothed out the shape and crystallized quantum fields, constants, and interaction strengths, similar to a cosmic artist. The rules of nature might not be eternal if this is true. Instead, they might be the result of a short period of excitement. This connects to the idea of vacuum selection. In quantum field theory, there are often many possible vacuum states a field can settle into, each with different properties and laws. Think of it like a marble on a hilly landscape. Where it ends up rolling determines the rules that will follow. Inflation may have tilted the landscape just right to guide our universe into the vacuum state we now live in. In some models, especially eternal inflation, space is constantly inflating in different regions. Tiny pockets pop out of the inflating fabric, each with their own vacuum states. These become bubble universes, each with potentially different laws, constants, and particles. That's the multiverse theory, and inflation is its engine. If that's true, then the laws of our universe aren't the only possible ones. They're just the result of our particular bubble settling into a certain configuration during its inflationary birth. Others may have wildly different laws, some with no gravity, others with faster light speed, or different forms of matter entirely. But let's not dwell on the unknown. What does inflation really explain in words that we can see? To begin, there were the small waves it made. During inflation, quantum fluctuations, which are usually very small, were spread out over very long lengths in space. These changes led to the formation of galaxies, clusters, and filaments, which are all types of organization in the universe. We wouldn't have the right kind of density changes to understand the big picture of the universe without inflation. And we've seen these ripples. The cosmic microwave background, a faint glow from 380,000 years after the Big Bang, contains temperature variations that match the statistical patterns predicted by inflation. The power spectrum of those fluctuations is one of the strongest pieces of evidence for the theory. We don't know what the inflaton field actually is. We don't know how inflation ended, the so-called reheating phase. And we don't know whether its dynamics really dictated the constants and forces we see. Multiverse hypotheses. Are there other law sets? Think about a world where gravity is 10 times stronger, stars never form, and atoms smash into each other. or one where light moves more slowly and the world feels like it's moving more like molasses. These aren't made-up scenarios from science fiction. They're real options brought up by the multiverse, one of the most strange ideas in modern physics. At the heart of this idea is a question that shakes the very roots of science. Are the laws of physics really the same everywhere? Or are they only rules that apply in this area and not elsewhere? The multiverse hypothesis suggests that our universe might be just one bubble in a vast cosmic foam, a single region with its own set of physical laws, constants and particles, surrounded by countless others, each playing by entirely different rules. It all starts with cosmic inflation. As we saw in the previous chapter, inflation is the idea that right after the Big Bang, the universe expanded exponentially in size. But some models, like eternal inflation, suggest that this process never fully stopped. Instead, it continues in other regions of space. Each time inflation slows down in a patch, that patch becomes a new universe, or bubble universe, with its own unique vacuum state. Why does this matter? The forces of nature act a certain way depending on the vacuum state, whether or not particles have mass, if atoms can come together, if life is even possible. That is, each bubble might come out of the inflationary field in a unique way, like marbles rolling down a hill and falling in a different valley. In each world, this means that the rules of physics are different. There may be no electromagnetic field in some bubbles. Some may not have the strong nuclear force. Some might have dark matter that acts in a way that is very different from ours. In this view, the so-called constants of nature, like the fine structure constant, the strength of gravity, or the mass of the Higgs boson, aren't constant at all. They're local environmental variables. Our universe just happens to have values that allow complexity, chemistry, and consciousness to emerge. The interesting and irritating thing about the multiverse theory is that it doesn't explain anything for sure. Why does gravity have the strength that we see? Because in universes with a lot more energy, stars either burn out right away or never form at all, which means that people like us can't live there and ask the question. Theories say that the cosmic constant, or dark energy, should be very large, but it is very small. Galaxies can't form in worlds that are bigger than this one. This line of thinking is known as the anthropic principle, a selection effect. We observe a universe compatible with life because only such universes contain observers. It's not an explanation in the traditional sense. It's a filter. Another comes from string theory, which posits an enormous landscape of possible vacuum states, on the order of 10 to the 500 different configurations. Each one corresponds to a universe with different dimensional shapes, particle types, and force strengths. Our universe could simply be one selection from this vast menu, chosen not by design, but by statistical inevitability. Then there's the quantum multiverse, born from the many worlds interpretation of quantum mechanics. According to this view, every quantum event branches reality into multiple outcomes. Flip a quantum coin, and the universe splits, one where it lands heads, one tails. This doesn't necessarily create different physical laws, but it creates divergent histories, where the same starting laws play out in every possible way. These thoughts aren't just idle speculations, not because scientists want them to be true, but because some ideas need them to make sense. They're becoming more popular in standard physics. It helps to explain why our universe is so fine-tuned for life. It could be the only game in town, or it could be the only place to play that game. The biggest challenge? Falsifiability. If we can never observe another universe, how do we know they exist? Is the multiverse a scientific theory, or a philosophical one wearing a lab coat? Some researchers are looking for indirect signs. For example, collisions between bubble universes during the inflationary epoch might leave faint circular scars in the cosmic microwave background. Others look for statistical anomalies in cosmological data, patterns that might hint we're just one realization out of many. But so far, no conclusive evidence. Anthropic filtering. Did laws favor observers? It's true that our world is incredibly useful. It's just the right amount of gravity for stars to form without falling apart right away. Atoms can exist because of the electric force. There is less than a 1 part in 1,000 difference in weight between the neutron and the proton. This is what makes hydrogen fixed and powers stars. What about the cosmic constant? That's way too small, but not zero. It's just the right size to let galaxies form without breaking apart. Real life seems perfectly tuned for complexity, chemistry, and finally life itself, everywhere we look. This uncanny balance has puzzled physicists for decades, because most combinations of fundamental constants would lead to dead, empty universes. Universes where atoms don't stick, where stars never shine, where expansion is too fast or collapse too sudden. So the question is, why these laws? Why these constants? Enter the anthropic principle, a concept as controversial as it is provocative. At its core, the anthropic principle says this: the universe looks the way it does because if it didn't, we wouldn't be here to notice. In other words, there's selection bias baked into our cosmic observations. We're not seeing the whole picture. We're seeing the tiny subset of possibilities that allow observers like us to exist. This idea gained momentum with the rise of multiverse theories, as explored in the last chapter. If there are countless universes out there, each with slightly different physical constants or force strengths, then it's no surprise we find ourselves in the rare one that's just right. Most universes might be sterile. Ours is special, not because it was chosen or designed, but because it's one of the few that can support complexity long enough for consciousness to emerge. The strong anthropic principle goes even further and says that the world must have features that make it possible for people to watch it. This leaves the door open for teleological explanations, which say the world is forced in some way to create life. This version doesn't sit well with most scientists. It smells too much like a point or plan, which is not what science is about. Most people agree with the weak anthropic principle instead. That doesn't mean the world has to be able to support life. It just means that our observations are limited by the fact that we are here. Still, even the weak version has power. It can help explain why the cosmological constant is so small. As Nobel laureate Steven Weinberg pointed out, if it were even a few hundred times larger, galaxies wouldn't form. And yet, here we are, galaxy dwellers. The anthropic principle doesn't predict the exact value, but it sets a boundary. It tells us that large values are overwhelmingly more common across the multiverse, but they're invisible to us because they don't support observers. This line of reasoning is uncomfortable for many scientists. It feels unsatisfying, like giving up on a real explanation. Anthropic arguments don't provide mechanisms. They don't derive laws from first principles. They just say, you're in the subset of universes where you could be. That might not be very classy. It could be true, though. There are comparisons that help you understand this better. Picture a fish in a pond. There might be a lot of water around, and the fish might wonder why it's so nice to swim. But those aren't just random events. They're the way things are. The fish wouldn't be in the water if it was hot. The fish would never form if the pond were dry. So the question is the pond unique? Or are the fish just seeing a place where they can survive? The anthropic principle works the same way. We're cosmic fish. We're looking around and wondering why everything is so perfectly calibrated. But maybe it's not perfect. Maybe it's just survivable. Maybe we evolved in a narrow sliver of possibility, and that sliver feels like a miracle only because we can ask about it. Now, this principle gets more useful when paired with probability. Some researchers build probability distributions over possible constants, like the mass of the electron or the density of dark energy, and then see how likely life-friendly values are. The results are striking. Life-permitting ranges are razor-thin, but not zero. And the fact that we fall within those ranges suggests anthropic filtering is doing real work. And it's not just particle physics. Cosmology, too, seems to favor a Goldilocks zone. The age of the universe is about 13.8 billion years. Coincidentally, that's just the right timescale for star formation. heavy element accumulation, and biological evolution to play out. If we lived in a younger universe, we wouldn't exist. If it were much older, stars might be burned out. The number of dimensions in space is also important. When there are more than 3 dimensions, gravity acts in different ways. There are no stable paths. It's not possible to do difficult science in less than 3. Once more, we're in the rare situation where structure can form, stay put, and finally start to ask questions. Critics argue that anthropic reasoning isn't science. It lacks predictive power. It can explain any observation after the fact. And it often feels like a cop-out when deeper theories are hard to find. What if we simply don't understand the real mechanism yet? What if fine-tuning has a hidden cause that anthropic arguments obscure? Effective theories. Are our laws just temporary models? The beautiful thing about physics is that it finds equations that work everywhere, all the time. What if, though, those numbers aren't always true? Would it be possible that they are just good ideas or models that work well in a certain area, but not in others? It's not going backwards. It's possible that this is how science has always worked. Newton's laws of motion were once considered universal. They predicted falling apples and orbiting planets with stunning precision. But then came Einstein, who showed that at very high speeds or strong gravitational fields, Newton's equations fail. They're not wrong, but they're not complete. They're effective, a good approximation in the low-speed, low-gravity world we usually live in. The same goes for classical thermodynamics, which works beautifully to describe heat and energy flow, until you zoom in far enough to see the atomic dance underneath. Then, statistical mechanics takes over. And even quantum mechanics, the crown jewel of 20th century physics, might itself be an effective description of something deeper. So what exactly is an effective theory? It's a model that describes behavior at a certain scale or under certain conditions, without claiming to explain what's happening at all levels of reality. Think of it like using weather maps. They predict rain and temperature without tracking every air molecule. That doesn't make them useless. It makes them powerful within their domain. The idea of effective theories is now central in modern physics. We build models that work at the energy scales we can test. But we always suspect they're shadows of something deeper. The standard model of particle physics, for example, is incredibly accurate. Yet everyone agrees it's incomplete. It leaves out gravity, dark matter, dark energy, and gives no reason for its 19 free parameters, like quark masses and force strengths. It works, but it doesn't explain. Effective field theories, EFTs, don't just tolerate ignorance, they embrace it. In fact, EFTs are built on the idea that we don't need to know what's going on at ultra-high energies to make accurate predictions at low energies. As long as we respect the symmetries and known behaviors, we can write down a theory that works, even if the ultimate laws remain hidden behind a veil of energy we can't yet pierce. This mindset has been astonishingly productive. It's how we deal with nuclear forces, condensed matter systems, and even inflationary cosmology. It's a philosophy of humility. Model what you can, where you can, and don't pretend it's the final answer. If every rule works, then none of them are final. Every idea is only a guess. There is a limited fact for every equation. Not even Einstein's general theory can explain everything. It breaks down at singularities and the Planck scale. In a quantum theory of space-time, the equations that describe gravity so well might not work at all. This isn't just a guess. Space-time could appear on its own in string theory and other theories of quantum gravity. That would mean that general relativity is just a good way to describe something more basic, like how thermodynamics is for atoms. Everything we know about particles is based on quantum field theory, which might be the same. It could be a scientific average of something more complex, like the images that make up a picture. Some physicists take this even further. They argue that space, time, mass, and even causality might all be emergent features, convenient illusions that arise from deeper information structures. This puts us in a strange position. Our deepest truths might be approximations. Our laws might just be useful lies, tools that work but aren't rooted in the base code of reality. That's not a reason to give up, though. In fact, the opposite. It means the universe might have more colors and shapes than we thought. There are new rules, patterns, and similarities revealed by each layer. And science is no longer a search for a clear answer, but a trip through these layers to learn more about how reality changes at different scales. There's also beauty in ideas that work. They show that you don't need a full picture to understand complexity. Quantum electrodynamics says that your phone follows its rules, but the expert who made it doesn't have to answer Schrödinger's equation for each electron. The rules of how semiconductors work are enough. The world we live in is made up of many close estimates, but it works perfectly. Of course, this also means we need to be cautious. When a theory works really well, we tend to assume it's universal, but that's an illusion. The map is not the territory. And as we push into new frontiers, black holes, the early universe, ultra-high energies, we may find that today's laws fade, bend, or break. This is already happening. Observations at cosmic scales hint that general relativity might not explain everything. Dark energy and dark matter don't fit comfortably into existing frameworks. Neutrino oscillations broke the Standard Model's rules. The muon's magnetic moment is off by just enough to whisper, something's missing. Can particles violate the laws? Quantum anomalies. A comforting thought lies at the heart of physics. Rules are followed. Energy should be kept the same. Charge stays the same. There are rules of symmetry that keep the world in order and dependable. What if, though, nature breaks its own rules just when it needs to? To be clear, anomalies in physics don't mean mistakes or glitches. In fact, they arise from the most rigorous mathematical procedures. You start with a theory that respects certain symmetries, like conservation of charge or parity. You do the math, quantize the fields, calculate interactions, and suddenly, those symmetries vanish. Not because you did something wrong, but because quantum mechanics rewrites the rulebook at the smallest scales. The chiral oddity is one of the oldest and best-known cases. Classical field theory says that some objects, like massless fermions, should keep something called chiral symmetry. Think of it like handedness. Particles that are left-handed and particles that are right-handed should behave the same way. This consistency breaks down, though, when quantum effects are added. As a result, theories that were meant to keep particles safe suddenly break down in ways that shouldn't be possible. This isn't just a guess. The chiral anomaly is the only thing that can explain how the neutral pion, pi, can break down into two photons. The process that was seen would still be a riddle without this breaking of the rules. To put it another way, quantum law breaking is necessary for our world to work. Another striking case is the gauge anomaly. In quantum field theory, gauge symmetries are sacred. They define the forces themselves. If an anomaly creeps in and disrupts this symmetry, the theory becomes inconsistent. It's like having a bridge with a missing support beam. Collapse is inevitable. That's why the Standard Model of particle physics is constructed with extreme care to ensure all gauge anomalies cancel out. The very structure of known physics is balanced on a tightrope of anomaly cancellation. Strange things don't just break the rules, they can also keep them safe. In the topological quantum field theory, strange things called anomalies can make states of matter that wouldn't be possible without breaking the symmetry. They help explain why some systems are so steady, like some quantum Hall effects that show up in two-dimensional electron systems when conditions are very bad. These strange phases exist because the idea behind them is strange. The violation turns into a sign of security. Think of it like jazz. A note played off-key in a classical symphony might ruin the music, but in jazz, that same dissonant note creates flavor, depth, and unexpected beauty. Anomalies are quantum jazz. They play with the rules to create something new. Also, people are becoming more and more worried that strange events could lead us to new physics. Take the most latest tests with muon G2. The standard model doesn't quite match up with the moon's magnetic moment, which is how it wobbles in a magnetic field. That small difference could be the sign of something strange, the imprint of particles or forces we don't fully understand. The same goes for dark matter. If there are particles outside of the standard model, they might create new oddities or need new symmetry corrections. We might find whole new parts of reality by looking into where the math fails. Gravitational anomalies suggest that under certain exotic conditions, like in early universe cosmology or near black hole singularities, space-time itself might fail to conserve quantities we assumed were sacred. Some versions of string theory depend critically on anomaly cancellation in higher dimensional space to remain consistent. In this way, anomalies become the architects of possible universes. This makes us realize something very important. Rules aren't always right. They come from patterns that only hold true if certain things happen, and quantum abnormalities show where that connection isn't quite right. Because nature is based on chaos and chance, these things show us that what we call laws are actually the best promises it can make. So why don't we see particles breaking the rules every day about charge or energy? Because most strange things are very slight. They only show up in certain energy conditions, systems that are limited, or mathematical models of extreme settings, but they're always there, waiting and giving hints, as if there were holes in a cosmic contract. Why is the universe mathematical? The mystery of predictability. The question of why math works so well to explain the world is one of the most puzzling in all of science. Why do the way planets orbit, particles behave, and galaxies grow so perfectly match up with models that people made up? There's no reason math should be able to predict the future behavior of physical systems. And yet, it does, spectacularly. We can use a few symbols on a chalkboard to launch spacecraft, forecast eclipses centuries in advance, or simulate black hole collisions on supercomputers. Even the discovery of the Higgs boson at CERN wasn't a lucky find. It was predicted decades in advance using nothing but math. The more you think about it, the weirder it gets. Math is a human invention, or at least a human language. It's not made of atoms or fields. It doesn't grow on trees or orbit stars. Yet somehow it appears to be the blueprint of reality itself. This eerie alignment was famously described by Nobel-winning physicist Eugene Wigner as the unreasonable effectiveness of mathematics in the natural sciences. He wasn't being poetic. He was baffled. Why should equations born from logic and creativity map onto the raw behavior of the cosmos? Start with Newton's laws. His equations of motion could predict the position of a planet hundreds of years into the future. Then you have Maxwell's equations, which describe electromagnetism. Written down in the 1860s, they predicted the existence of radio waves decades before anyone knew what they were. Einstein's equations of general relativity not only predicted black holes, they predicted how light would bend around massive objects long before the first observations confirmed it. And quantum mechanics? It's pure math, yet it powers everything from lasers to MRI machines to the chips in your phone. Schrödinger's equation doesn't just describe atoms, it tells us exactly how electrons live around a nucleus. What's going on here then? The idea that the universe is based on math is one option. That math doesn't just describe nature, it is nature. This is the bold claim that some scientists make, like Max Tegmark, who says the world is made up of numbers. From this point of view, everything from quarks to awareness comes from the way numbers, sets, and geometric shapes are put together. It's a big step, but it's been done before. In physics, geometry has always been very important. The universe works like a well-written equation, from the paths of the planets to the curve of space-time. Higher dimensional math is used to build everything, even string theory, which is our best hope for a theory of everything. Another possibility is that we're only seeing the math that works, that our brains evolved in a universe where certain patterns are predictable and our math reflects those patterns. In this view, math is effective because we've tailored it to the slice of reality we can observe. Beyond that slice, who knows? Then there's the anthropic argument. Maybe only in universes where math works can beings like us evolve to notice it. If math didn't match reality, we wouldn't be here asking questions. This doesn't explain why it works, but it does suggest that our existence filters out the alternatives. In physics, math often leads the way. We don't just observe phenomena and then find equations to match. Often we discover new physics by following the math itself. When Dirac wrote down his relativistic equation for the electron, he found that it allowed for a bizarre new particle, the positron. No one had ever seen one, but a few years later, it was detected in a cosmic ray experiment. The Higgs boson is the same way. The same goes for gravitational waves. Math came first, and then nature came next. So, did math get found, or was it invented? Philosophers and scientists are still not sure how to answer that question. Some people say that mathematical facts already exist and are just waiting to be found, like fossils in the desert. Some people say we make them up by creating imaginary systems that work with nature by chance. Either way, the predictive power of math is undeniable, and not just in physics. Biology, chemistry, even social sciences use mathematical models to describe behavior and evolution. The fractal geometry of a fern leaf, the statistical patterns of city growth, the symmetry of DNA. All of it echoes a mathematical rhythm that pulses beneath the surface. Maybe that's the answer. Maybe math is the best language we've found to capture patterns, and the universe, at its core, is made of patterns. Not because it's trying to be mathematical, but because structure and relation are how reality sustains itself. But there's something creepy about how math can explain places we've never seen. It will be a long time before our telescopes can write down the shape of a 10-dimensional space or figure out how a neutron-star merger works. We can figure out how much energy virtual particles have that appear and disappear quickly. These events are not just random. These are signs that math isn't just going along for the ride. It's showing a structure that was hidden. Some of the best ideas, like quantum chromodynamics, are very hard to understand. Others, like the Standard Model, work great, but the choices they make about their parameters seem random. Group theory, tensor calculus, and differential geometry are just a few of the math tools that can help us make sense of this mess. The hierarchy problem. Why is gravity so weak? Out of all the fundamental forces in the universe, electromagnetism, the strong force, the weak force, and gravity, one stands out as the runt of the litter. Gravity, despite shaping the motion of galaxies and anchoring us to the Earth, is mind-bogglingly weak at the particle level. To put it bluntly, gravity is around 10 to the 36th power times weaker than the strong nuclear force. That's one followed by 36 zeros. It's not just a little weaker, it's absurdly weaker. And that imbalance is one of the biggest open mysteries in modern physics. This is what scientists call the hierarchy problem. Why the forces of nature have such dramatically different strengths, and specifically, why gravity is so pathetically feeble compared to the rest. We don't really notice this weakness in everyday life because gravity acts on mass, and we experience it all the time. Drop your phone and gravity's there. But that's only because gravity has infinite range and only comes in one charge, mass energy. Meanwhile, the electromagnetic force can both attract and repel, so large-scale objects like people or planets usually cancel out their electric charges, but they never cancel out mass. That's why gravity always seems dominant on large scales. But zoom in, and you'll see how hopelessly weak it really is. If you hold a paperclip near a magnet, the magnet easily overcomes the entire gravitational pull of the Earth. That's trillions of metric tons, defeated by a fridge magnet. Let that sink in. So where does this lopsided scale come from? The Standard Model of particle physics explains 3 of the 4 forces with extraordinary precision. But gravity is left out. It's not part of the quantum framework. And the Higgs mechanism, which gives particles their masses, adds another layer to the puzzle. Quantum corrections to the Higgs boson mass should be enormous. So big, in fact, that unless some unknown mechanism is fine-tuning things with precision beyond comprehension, The Higgs should weigh more than the entire universe, and yet its measured mass is just 125 giga-electron volts. This seems suspiciously clean. It's like balancing a pencil on its tip in a hurricane and having it stay upright for 13.8 billion years. Fine-tuning is the method that scientists use to get rid of very large numbers with great accuracy in order to keep the Higgs mass at that low level. That doesn't feel real. Scientists don't like it. Why should nature need to do something so strange to keep things in balance? Supersymmetry is a well-known one. That each known particle has a larger superpartner that cancels out the extreme quantum adjustments to the Higgs mass is what this idea says. These superpartners would make the math more stable, explain why gravity is so weak, and maybe even explain dark matter. But after years of looking, mostly at the Large Hadron Collider, we haven't found solid proof of these superparticles, at least not yet. Another idea involves extra dimensions. If space has more dimensions than the three we experience, plus time, then gravity might be leaking into these hidden dimensions, diluting its strength in our visible universe. Imagine trying to pour water into a flat dish, but the dish has secret holes underneath. Most of the water escapes, leaving only a trickle on the surface. This is the core of theories like brane world scenarios, including the famous Randall-Sundrum model, which postulates that our universe is a 4D membrane floating in a higher dimensional bulk. Technicolor theories are another idea. These are models that try to get rid of the Higgs completely by seeing mass as the result of a new strong interaction. But it's hard to prove these ideas with exact numbers, and a lot of them have lost popularity. Some people also think that gravity isn't a fundamental force, but something that just happens. This way of thinking says that gravity might be a large-scale effect, like pressure or temperature, that comes from the way that very small quantum degrees of freedom behave when put together. Eric Verlinde, a Dutch scientist, came up with a theory called entropic gravity, which says that gravity is caused by changes in the information about where particles are. That is a crazy way of thinking, but it might help when your numbers start to break down at the smallest sizes. Do black holes follow the laws or rewrite them? Black holes are thought to be the hardest things in all of science. A place where mass falls apart, time bends, and gravity rules supreme. The interesting thing is that they look more and more like rebels as we get closer. They look like cosmic outlaws who question, bend, and maybe even break the rules they're supposed to follow. Let's start with what we do know. Black holes are regions of space-time so warped by gravity that nothing, not even light, can escape once it crosses the event horizon. General relativity predicts them. We've seen their shadows with the Event Horizon Telescope. We've watched stars orbit around the one at the center of our Milky Way. They're real. They're out there. But they don't play nice with the rest of our theories. In classical physics, the laws of conservation, of energy, momentum, and information are sacred. But when matter falls into a black hole, it seems to vanish without a trace. Burn a book, and you can still, in principle, recover the information from the smoke and ash. Toss that book into a black hole. Game over. It's as if the universe just deletes the file. This is the infamous black hole information paradox. Stephen Hawking brought it into the spotlight when he showed that black holes aren't entirely black. They emit faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. But this radiation is thermal, random. It carries no information about what fell in. So if a black hole evaporates entirely, the information inside appears lost forever. That breaks the law of unitarity in quantum mechanics, which says information is never destroyed, just transformed. If black holes destroy it, quantum theory takes a hit. But if quantum theory is right, then black holes must somehow preserve or return that information. So which is it? Physicists have proposed many possible fixes. One idea is that information is stored on the event horizon, encoded in two-dimensional surface data, not inside the black hole. This concept evolved into the holographic principle, which suggests that all the information in a volume of space can be represented by a theory on its boundary. It's like reality is a 3D projection of 2D data, similar to how a hologram works. In this view, the black hole doesn't destroy information, it just stores it on its surface in a scrambled form. Others say that unknown quantum gravity effects happen at the edge of the event horizon and keep information safe in ways we can't yet see. Or that Hawking radiation isn't completely random, but has tiny, linked traces of what's inside, like a quantum whisper escaping into the universe. What if black holes don't really evaporate? Or what if they leave behind remnants, tiny, indestructible cores where information remains? These raise their own problems, like infinite varieties of remnants cluttering up the universe. Another proposal is the firewall paradox, suggesting that the event horizon isn't smooth, but instead a blazing inferno of quantum energy that burns up any infalling matter. This breaks the equivalence principle in general relativity, which says you shouldn't feel anything special when crossing the horizon. So now one law contradicts another. Some theories propose that the interior of a black hole is connected to the outside world via a quantum wormhole, a solution popularized as ER, equal sign EPR. This suggests that every pair of entangled particles is linked by a microscopic wormhole, and black holes use this connection to offload information. It's mind-bending, but surprisingly elegant, merging relativity and quantum mechanics in unexpected ways. Even though this is all very smart on paper, we're still not sure what's going on. To the point, it's easy to keep secrets in the event horizon. We can't look inside. We can't use real black holes for tests. Also, no one has yet found a clear signal in Hawking radiation that shows data does get out. Why does it matter then? If black holes really do break the rules, then those rules aren't as important as we thought. There's a chance that general relativity is just a rough guess. Quantum physics might need to be improved. Maybe there is something missing from the way we think about space-time, gravity, and information as a whole. Maybe black holes don't break the rules, they just show us what they are, letting us see the cracks in our models. As testbeds for the next big change in physics, that is. A lot of researchers think that the black hole riddle needs to be solved in order to find a theory that explains everything, including gravity, quantum fields, and the structure of space-time itself. Neutrinos. Do ghost particles obey the same laws? Neutrinos are like ghosts in the world of particles. They fly through walls, planets, and even whole stars as if they aren't even in this world. They have almost no mass, are electrically neutral, and are very hard to find. Still, they are everywhere. Each second, trillions of them pass through your body in a silent flood of cosmic data. Despite being among the most elusive particles we know, neutrinos may be violating, or at least bending, some of the most sacred laws in physics, and that makes them one of the best tools we have for peeking behind the curtain of the known universe. Neutrinos were first theorized, not observed. In the 1930s, physicists were puzzled by a mysterious loss of energy during beta decay, a type of radioactive decay. The conservation of energy seemed to be violated. That's a big no-no. To fix it, Wolfgang Pauli proposed a desperate remedy, an invisible particle that carried away the missing energy. That was the neutrino. For decades, they were practically undetectable, mere ghosts in math. But eventually, we caught them. In 1956, Clyde Cowan and Frederick Rains detected neutrinos from a nuclear reactor, and these wispy ghosts became real members of the standard model of particle physics. Originally, neutrinos were thought to be massless, but in the late 1990s, experiments in Japan and Canada, Super Kamiokande and SNO, respectively, showed something shocking. Neutrinos oscillate. They change flavor, electron, muon, tau, as they travel. And the only way this is possible is if they have mass. That broke the standard model. Not totally, but enough to show that something deeper was going on. Neutrinos don't just defy detection, they defy expectations. What does this mean? Neutrinos have mass, even if it's very small, which means that our current idea isn't complete. Neutrino mass is not taken into account by the standard model. Either the model needs to be made bigger, or there is a secret mechanism at work, such as the so-called seesaw mechanism, which involves neutrinos that are very heavy but that we have never seen. The thought of sterile neutrinos is even stranger. Different from the three types that are already known, sterile neutrinos would not interact with any of the known forces except for gravity. They would be even stranger than normal neutrinos. If they exist, they might be a part of dark matter, connecting what we can see with the universe's mass that we can't see. Then there's the matter-antimatter problem. Our universe is dominated by matter, but the laws of physics suggest it should have created equal amounts of antimatter. So where did all the antimatter go? One theory points to neutrinos. If they violate a symmetry called CP symmetry, which treats matter and antimatter as interchangeable, they might help explain why our universe didn't self-destruct in a flash of mutual annihilation. Experiments like NOVA and DUNE are currently probing this very idea. Neutrinos could be their own antiparticles. That is, a neutrino and an antineutrino might be the same thing. If that's true, and it's called the Majorana hypothesis, it would mean that the universe contains particles that violate the conservation of certain quantum numbers. It would also open the door to neutrinoless double beta decay, a rare process that researchers are now desperately trying to observe. Let's not forget neutrinos' cosmic origins either. They're birthed in fusion reactions inside stars, in exploding supernovae, and in the first moments of the Big Bang. The cosmic neutrino background, relics from the universe's first seconds, is still floating around us, whispering secrets about those primordial times. We also detect neutrinos from deep space using instruments like IceCube in Antarctica. When these ultra-high-energy neutrinos hit our detectors, they give us a new kind of astronomy, one that doesn't rely on light at all. This neutrino astronomy could one day help us map distant galaxies, supernova remnants, or even black hole mergers in a totally new way. Yet for all their cosmic reach and fundamental weirdness, neutrinos remain maddeningly hard to study. They rarely interact with other particles. You can build a detector the size of a skyscraper and only catch a few neutrinos per day. But everyone is a breadcrumb, pointing toward physics we don't yet understand. What does it mean to ask, do ghost particles follow the same rules? It's possible that the answer is not quite. There are rules that neutrinos follow, but they might not be our rules. Or maybe they're following rules we haven't fully figured out yet. Their strange behavior, mass without a reason, variation without a reason, and an identity that might change indicates that they're following a bigger plan. One that makes hints at big unification, secret dimensions, or whole new areas of physics. Can we derive all laws from information? It's possible that everything you know, including particles, forces, time, and space itself, is not made of matter. What if knowledge is what the world is made of? This is no longer just an intellectual thought. Theoretical physics has a real question that is becoming more important. Is knowledge the most basic thing that exists? More importantly, can the holy rules that guide the world, the laws of physics, be derived not from fields or particles, but from how information is stored, changed, and kept? It might sound like science fiction, but this line of thinking is gaining ground fast. The idea has roots in black hole physics, deep links to quantum theory, and shocking implications for the nature of reality itself. Stephen Hawking's work in the 1970s showed that black holes emit radiation, what we now call Hawking radiation. Over time, this causes black holes to slowly evaporate. But here's the problem. If a black hole swallows matter and then disappears into nothing, where does the information about that matter go? This sparked the infamous black hole information paradox, a clash between general relativity, which says black holes destroy information, and quantum mechanics, which says information is always conserved. Decades of debate followed. Then came a bombshell insight. Maybe black holes don't destroy information at all. Maybe the information is encoded on the event horizon, the boundary of the black hole, and slowly leaks out with the radiation. This is the holographic principle, and it flipped the game. The holographic principle says that everything happening in a volume of space can be described by information encoded on its boundary, like a 3D image stored on a 2D surface. The implication: space itself might be emergent, not fundamental, but something that arises from deeper information structures. All of a sudden, anything was fair game. What if gravity comes from the way that data is spread out in space? It's possible that an object's mass shows how much information it takes to explain its internal state. What if time is just the way that direct links between data points play out? This led to what many now call the information-first paradigm. Instead of trying to write down better equations about particles or fields, theorists are asking, what are the rules that govern information in the universe? And can those rules generate physics as we know it? Take quantum entanglement, for instance. When two particles are entangled, measuring one instantly gives you information about the other, no matter how far apart they are. This has led some to suggest that space-time itself is stitched together by entanglement. That is, the fabric of the universe is literally woven from shared information. In this view, distance doesn't come first, information flow does. Space is just a map of which systems can share information easily and which can't. The closer two regions are in this information geometry, the more easily they can communicate. Then there's ADAS-CFT correspondence, one of the most powerful dualities in modern physics. It shows that a gravitational universe in 5 dimensions can be fully described by a quantum theory on its 4-dimensional boundary. Again, information on the surface describing everything inside. The math works. It's not a metaphor, it's a map from gravity to pure data. Physicist Eric Verlinde has even proposed that gravity itself is not a force, but an entropic effect, something that emerges when systems seek to maximize their informational entropy. This flips Newton's apple on its head. The apple didn't fall because of a force. It fell because the universe was reshuffling its information. In parallel, thinkers like Seth Lloyd, Gerard 't Hooft, and John Wheeler have pushed variations of this idea, from the universe is a quantum computer to it from bit, the notion that every physical thing arises from binary yes/no information at the most basic level. How far can this go? Some theorists think that one day we could use the basic rules of how information works to infer all known physical laws, like Einstein's theory of relativity, quantum field theory, and thermodynamics. Not a big equation for everything, but a deep knowledge that everything is a reflection of data would be the best way to bring everything together. This method isn't just vague. It might change the way we think about measures, awareness, the real world, and computer games. There might be a limit to the world if it is a computer system. Pixels could be in it. Yes, it might even be able to be programmed. In a universe where even the void hums with hidden logic, the question isn't just what the laws of physics are, but why they exist at all. From symmetry to entropy, black holes to information theory, we're peeling back the layers of reality one idea at a time. If this journey made you rethink everything you thought you knew about the cosmos, hit that subscribe button and keep exploring with us. This is Beyond Horizons, where the edge of science meets the unknown.